Earth's deep past holds catastrophes so immense they reshaped the entire planet. Around 252 million years ago, something killed roughly 96% of all marine species and 70% of terrestrial vertebrates, in what scientists call the Permian Triassic extinction, the closest life on Earth has ever come to complete annihilation. 50 million years later, an asteroid 6 miles wide slammed into what is now Mexico's Yucatan Peninsula, releasing energy equivalent to 10 billion Hiroshima bombs and ending the age of dinosaurs in a geological instant. Between these bookend disasters lie volcanic eruptions that darken skies for millennia, ice ages that encase the planet in glaciers from pole to equator, and climate swings so severe they boiled oceans or froze them solid. These aren't myth or speculation. They're written in rock layers, fossilized remains, and geochemical signatures that scientists have painstakingly decoded. Each event reveals how fragile the balance of life truly is, and how quickly our world can transform. 252 million years ago, Earth experienced a catastrophe so severe that scientists simply call it the Great Dying. The name isn't hyperbole. This event represents the closest complex life has ever come to complete extinction. A planetary crisis that killed an estimated 96% of all marine species and 70% of terrestrial vertebrate species. To put that in perspective, the asteroid that ended the dinosaurs eliminated roughly 75% of species. Devastating, certainly, but nowhere near the wholesale slaughter of the Permian Triassic boundary. When paleontologists first recognized this extinction horizon in rock formations worldwide, they struggled to comprehend what could have caused such thorough annihilation. The answer, pieced together over decades of research, points to a cascade of environmental disasters triggered by one of Earth's most catastrophic volcanic episodes. The Permian period had been a time of relative stability. Massive seed ferns called Glossopteris carpeted the southern supercontinent Gondwana, while bizarre synapsids, mammal-like reptiles that dominated terrestrial ecosystems, roamed forests and plains. In the oceans, complex reef systems built by sponges, corals, and calcifying organisms stretched across shallow continental shelves. Trilobites, those iconic arthropods that had survived for 270 million years through multiple extinction events, still scuttled across sea floors. Ammonoids spiraled through open waters, and primitive sharks patrolled deeper zones. Then, over a geologically brief period that may have lasted anywhere from 60,000 to 2 million years, researchers continued debating the exact time frame. Nearly all of it vanished. The primary culprit was volcanism on a scale almost unimaginable today. In what is now Siberia, a region covering roughly 770,000 square miles began erupting in a series of massive volcanic events that collectively formed what geologists call the Siberian Traps. The term trap comes from the Swedish word trappa, meaning steps, referring to the distinctive stair-like appearance of eroded flood basalt formations. These weren't cone-shaped volcanoes ejecting ash in explosive eruptions. Instead, imagine vast fissures in Earth's crust opening up, pouring out low-viscosity basaltic lava that flowed for hundreds of miles across the landscape, building layer upon layer of solidified rock that in some places reached thicknesses exceeding 1.2 miles. Recent uranium lead dating of zircon crystals within these basalts has refined the timing of eruptions, showing they began just before the extinction boundary and continued for roughly 1 million years. But lava alone couldn't kill 96% of marine life. The true devastation came from gases. As magma rose through Earth's crust, it encountered layers of coal, oil, and carbonate rocks, essentially fossil fuel deposits and limestone. The immense heat baked these sediments, releasing staggering quantities of carbon dioxide, methane, and sulfur dioxide into the atmosphere. Conservative estimates suggest the eruptions released between 30,000 and 40,000 gigatons of carbon dioxide over the course of the volcanic episode, roughly equivalent to burning all known fossil fuel reserves on Earth today several times over. Sulfur dioxide emissions may have exceeded 100,000 gigatons. Chemical analysis of ancient soil carbonates preserved from this period shows atmospheric carbon dioxide levels spike to concentrations more than 10 times higher than pre-industrial levels. The environmental consequences unfolded like dominoes. Sulfur dioxide aerosols initially cooled the planet by reflecting sunlight, potentially dropping global temperatures by several degrees for years to decades after major eruptive pulses. This would have stressed ecosystems already adapted to Permian warmth, but sulfur aerosols settle out of the atmosphere relatively quickly, typically within a few years. Carbon dioxide and methane, by contrast, remained for centuries to millennia. As sulfur levels dropped, the greenhouse gases took over, driving temperatures upward in a runaway warming event. Geological evidence from oxygen isotopes in marine fossils indicates tropical ocean. Surface temperatures may have exceeded 104 degrees hot, enough to approach the thermal tolerance limits of many marine organisms. Land temperatures in equatorial regions could have reached 140 degrees Celsius during summer months, making vast areas essentially uninhabitable for vertebrates. Ocean chemistry shifted catastrophically. Carbon dioxide dissolving into seawater forms carbonic acid, lowering pH in a process called ocean acidification. The same phenomenon concerning climate scientists today, but happening far more rapidly. Calcium carbonate, the mineral that organisms from corals to mollusks to plankton use to build shells and skeletons, dissolves in acidic water. The fossil record shows a stark collapse of calcifying organisms at the Permian Triassic boundary. Massive reef systems that had persisted for tens of millions of years simply ceased to exist. In their place, researchers find thick layers of microbial mats, simple bacterial communities that indicate the ocean had essentially regressed to a more primitive state not seen since before complex life evolved. Warming oceans created another lethal problem. Warm water holds less dissolved oxygen than cold water, a simple physical principle with catastrophic consequences. As ocean temperatures climbed, oxygen concentrations dropped, creating vast anoxic zones where marine life suffocated. Sediment cores from this period show distinctive chemical signatures of anoxia, high concentrations of iron sulfides, depleted uranium isotopes, and organic-rich black shales that indicate oxygen-starved conditions extended from shallow coastal waters into deeper ocean basins. Computer models reconstructing ocean circulation patterns suggest that warming disrupted the thermohaline circulation, the global conveyor belt of ocean currents driven by temperature and salinity differences. Without this circulation, mixing oxygenated surface waters into the deep ocean, vast volumes of seawater became oxygen-depleted dead zones. But the ocean didn't just lose oxygen. In the most severely anoxic conditions, bacteria that don't require oxygen began producing hydrogen sulfide, the compound responsible for the smell of rotten eggs and a potent poison. Normally, hydrogen sulfide remains locked in deep sediments where oxygen never penetrates. During the Permian Triassic crisis, geological evidence indicates hydrogen sulfide concentrations built up in deep waters and eventually reach surface layers. Biomarker molecules preserved in ancient rocks from this time period include compounds produced by purple and green sulfur bacteria, organisms that thrive only in hydrogen sulfide-rich, oxygen-free environments. Their presence in rocks representing shallow marine environments tells us these poisonous conditions extended throughout the water column. When hydrogen sulfide-laden water reached the surface, the gas would have bubbled into the atmosphere. Hydrogen sulfide is toxic to most oxygen-breathing life at concentrations as low as a few hundred parts per million. Atmospheric modeling suggests concentrations in coastal regions could have exceeded 1,000 parts per million during the worst phases of the extinction. Any terrestrial animals living near coastlines would have faced not just extreme heat, but poisonous air. The ozone layer would have suffered as well. Hydrogen sulfide reacts with and destroys ozone molecules. With a weakened ozone shield, harmful ultraviolet radiation would have penetrated to Earth's surface at much higher intensities, adding yet another stress to organisms already struggling with heat. Acid oceans and oxygen depletion on land. The extinction unfolded somewhat differently, but no less catastrophically. The fossil record shows diverse communities of synapsids, including predators like the saber-toothed gorgonops and herbivores like the pig-sized Lystrosaurus, abruptly giving way to vastlies. Impoverished assemblages dominated almost entirely by Lystrosaurus. This single genus, a stocky herbivore with a turtle-like beak and possibly semi-aquatic habits, somehow survived when nearly everything else perished. For millions of years after the extinction, Lystrosaurus fossils make up roughly 95% of all terrestrial vertebrate specimens found in rock formations from South Africa to Antarctica to China. Scientists theorize its survival may relate to its burrowing behavior and ability to tolerate low oxygen conditions, but the exact reasons remain debated. Plant communities collapsed as well. Glossopteris forests that had covered millions of square miles vanished almost entirely. Pollen and spore assemblages preserved in rock show a stark shift from diverse seed ferns and conifers to dominance by a few species of fungi. Some formations from the immediate aftermath of the extinction contain layers where fungal spores outnumber plant pollen and spores by ratios exceeding 1,000 to 1, a phenomenon some paleobotanists interpret as evidence of massive die-offs, creating enormous quantities of dead organic matter on which fungi thrived. Soils from this interval show evidence of intense erosion and instability, suggesting landscapes stripped of vegetation cover became vulnerable to severe erosion during storms. The extinction didn't happen uniformly across all environments or at a single moment. High-resolution dating and detailed stratigraphic analysis reveal a complex pattern with at least 2 or possibly 3 distinct pulses of extinction separated by brief intervals of tens of thousands of years. The first pulse appears to have hit marine ecosystems hardest, while terrestrial ecosystems suffered most severely during subsequent pulses. Some researchers propose that different phases of volcanic activity, each releasing different proportions of gases or affecting different climate systems, created these multiple waves of environmental stress. Others suggest that various ecosystems collapsed at different times, as cascading ecological effects propagated through food webs and between interconnected habitats. Recovery took an extraordinarily long time. While other mass extinctions show ecosystems rebounding within a few million years, the Permian Triassic event left Earth's biosphere impoverished for up to 10 million years. Coal deposits, formed from accumulated plant matter in swamps and forests, are essentially absent from rocks representing the first 10 million years of the Triassic period, suggesting terrestrial ecosystems remained too stressed or unproductive to generate significant peat accumulation. Reef ecosystems didn't fully recover until the Middle Triassic, roughly 10 million years after the extinction. The lingering effects suggest that environmental conditions remained hostile or highly unstable well after the initial volcanic eruptions ceased. Modern research continues refining our understanding of exactly how the extinction unfolded. In 2011, a team led by scientists at MIT analyzed sediment cores from marine sections in China and found evidence of rapid fluctuations in ocean chemistry occurring within thousands of years or less. The speed of these changes suggests that Earth's climate system crossed critical thresholds, triggering rapid transitions between different stable states rather than gradual degradation. When carbon dioxide levels reach certain concentrations, feedback loops can amplify warming. Melting permafrost releases more methane. Warming oceans release dissolved carbon dioxide. Dying vegetation stops absorbing carbon, and the system spirals toward a new, hotter equilibrium. The Permian Triassic event may represent the most extreme example of such runaway climate change in Earth's history with complex life present. One particularly sobering discovery involves the role of methane hydrates. These ice-like compounds form when methane becomes trapped in molecular cages of frozen water under high pressure and low temperature, typically found in seafloor sediments and Arctic permafrost. Modern oceans contain enormous quantities of methane hydrates. Estimates suggest several thousand gigatons of carbon locked in these deposits. When ocean temperatures rise or pressures decrease, the hydrates destabilize and release methane gas. Methane is a greenhouse gas roughly 25 to 80 times more potent than carbon dioxide over short timescales. Carbon isotope ratios in Permian Triassic boundary rocks show distinctive signatures consistent with massive methane release. Some researchers calculate that destabilization of methane hydrates could have released between 10,000 and 20,000 gigatons of carbon into the atmosphere and oceans within a few thousand years, creating a feedback loop where volcanic warming triggered methane release, which caused additional warming, which destabilized more hydrates. The extinction reveals uncomfortable truths about Earth's environmental systems. Once certain thresholds are crossed, natural processes can create feedback loops that resist stabilization. The Siberian Traps eruptions didn't continue at constant intensity for a million years. There were pauses and variations in activity. Yet the climate system didn't simply return to its previous state during these lulls. Instead, the planet appeared locked into hot, anoxic conditions for extended periods, even when volcanic emissions temporarily decreased. This suggests that once carbon dioxide exceeded certain atmospheric concentrations and warming past particular thresholds, the Earth system shifted into a different stable state that persisted. until enough carbon was removed from the atmosphere through weathering of rocks and burial and sediments, processes that operate over millions of years. The Great Dying also demonstrates the vulnerability of complex ecosystems to rapid environmental change. Species that had survived and thrived for tens or even hundreds of millions of years vanished within geological instants. Trilobites had endured 4 previous mass extinctions over 270 million years, adapting to ice ages, sea level changes, and previous volcanic episodes. Yet they couldn't survive the Permian Triassic crisis. The same pattern holds for countless other lineages. Evolutionary success over long timescales provided no guarantee of survival when environmental conditions changed rapidly enough. The organisms that did survive often weren't the most specialized or dominant forms, but rather those with generalist lifestyles, wide environmental tolerances, or simple body plans that required less energy and resources. Examining fossils from the immediate aftermath of the extinction reveals ecosystems functioning in drastically simplified ways. Food webs that had contained dozens of interacting species collapsed to simple chains with just a few links. Specialized predators disappeared, leaving only opportunistic omnivores. Filter-feeding organisms that required specific water chemistry vanished, replaced by simpler forms. The Triassic world that emerged from this bottleneck was, in many ways, biologically impoverished compared to the Permian world that preceded it. It took millions of years of evolution to regenerate the complexity and diversity that had been lost. Why did recovery take so long? Part of the answer lies in the severity of environmental disruption. As long as oceans remained hot, acidic, and oxygen depleted, ecological niches that had existed in the Permian couldn't be recolonized. Species diversity couldn't rebuild until environmental conditions stabilized sufficiently to support more specialized organisms. Additionally, with so few species surviving, the raw material for evolutionary diversification had been dramatically reduced. Evolution creates new species through variation and selection, acting on existing populations. When most populations have been eliminated, the process of rebuilding diversity simply takes longer. The Permian Triassic extinction stands as the most extreme example of how volcanic activity, climate change, ocean chemistry, and biological systems interact in complex and often catastrophic ways. It demonstrates that Earth's environment can undergo state changes so severe that they reshape the entire biosphere, and that recovery from such events operates on timescales millions of years long. For scientists studying past mass extinctions, the Great Dying serves as a stark reminder that the stability of Earth's environment that allows complex life to flourish is not guaranteed, and that pushing climate systems past critical thresholds can trigger cascading disasters that no amount of evolutionary adaptation can overcome in real time. 66 million years ago, on what would become the Yucatan Peninsula of Mexico, the Cretaceous period ended in fire and darkness. An asteroid roughly 6 miles in diameter, about the size of Mount Everest, struck Earth traveling approximately 45,000 miles per hour. The impact released energy estimated at 10 billion times the power of the atomic bomb dropped on Hiroshima, or roughly 100 million megatons of TNT. In less than a second, the asteroid vaporized itself along with thousands of cubic miles of rock, excavating a crater that would eventually measure 110 miles across and 12 miles deep. The Chicxulub impact, named for the small town near the center of the buried crater structure, represents the most thoroughly studied and widely known extinction event in Earth's history. It ended the 165 million year reign of non-avian dinosaurs and cleared ecological space for the rise of mammals, ultimately leading to humans. But the path from impact to extinction involved a cascade of environmental catastrophes that unfolded over hours, months, and years. The asteroid likely originated from the main asteroid belt between Mars and Jupiter, nudged out of a stable orbit by gravitational perturbations, and sent on a collision course with the inner solar system. As it entered Earth's atmosphere, friction with air molecules heated its surface to incandescence. The passage through the atmosphere took only a few seconds, far too brief for atmospheric drag to slow an object of such enormous mass. When it struck the shallow carbonate platform of the Yucatan, covered by perhaps 600 feet of water at the time, the kinetic energy converted instantly to heat and shock waves. Temperatures at the impact site exceeded 18,000 degrees, hot enough to vaporize rock. The asteroid itself ceased to exist as a solid object within milliseconds, converted to superheated plasma. The immediate destruction extended for hundreds of miles. Seismic waves radiating from the impact point likely exceeded magnitude 10 on the Richter scale, roughly 100 times more powerful than the largest earthquakes in recorded human history. These shock waves traveled through Earth's crust at several miles per second, causing violent ground motion that would have toppled any structures or forests within a 1,000-mile radius. Computer simulations suggest that in the first 10 seconds after impact, a wall of rock ejected from the crater rose to heights exceeding 15 miles, momentarily reaching into the stratosphere. This curtain of vaporized and molten rock expanded outward at speeds initially exceeding 10,000 miles per hour, incinerating everything in its path across the Gulf of Mexico and southern North America. The impact punched entirely through Earth's crust into the mantle below. Drilling projects conducted in the 1990s and 2000s retrieved core samples from the crater structure that show distinctive, shock-metamorphosed minerals, quartz crystals with parallel fracture patterns that form only under extreme pressures, and tektites, glassy spherules created when molten rock is ejected into the atmosphere and rapidly cooled. Radiometric dating of these materials using argon-argon and uranium-lead techniques consistently yields ages of 66.043 million years, plus or minus 11,000 years, precisely matching the age of the Cretaceous-Paleogene boundary found in rock formations worldwide. This temporal coincidence between impact and extinction effectively ended decades of scientific debate about what killed the dinosaurs. The geology of the impact site made the catastrophe worse. The Yucatan platform consists largely of limestone and anhydrite, calcium carbonate and calcium sulfate rocks formed from ancient marine sediments. When vaporized by impact energies, these rocks released massive quantities of carbon dioxide and sulfur dioxide directly into the upper atmosphere. Studies estimate that between 100 and 500 gigatons of sulfur compounds were injected into the stratosphere within minutes of impact. For comparison, the 1991 eruption of Mount Pinatubo, which caused measurable global cooling, released approximately 20 megatons of sulfur dioxide, roughly 5,000 to 25,000 times less than Chicxulub. Additionally, the impact vaporized between 50 and 100 gigatons of carbonates, releasing carbon dioxide, and likely ignited global wildfires that released thousands of additional gigatons of carbon from burning forests. Tsunamis generated by the impact raced across shallow Cretaceous seas. Geological evidence from coastal deposits in Texas, Alabama, and New Jersey shows tsunami deposits, chaotic mixtures of marine and terrestrial materials, up to 15 feet thick at the Cretaceous-Paleogene boundary. Wave heights may have exceeded 300 feet near the impact site, diminishing to perhaps 30 to 100 feet along the eastern coast of North America and Caribbean islands. These waves would have reached coastlines within hours of impact, stripping vegetation, drowning coastal lowlands, and depositing debris fields containing everything from marine fossils to land plants and dinosaur remains jumbled together. Perhaps the most devastating immediate effect came from ejecta, the millions of tons of rock blasted into space by the impact. Material ejected at velocities exceeding escape velocity left Earth's atmosphere entirely, but much of it followed ballistic trajectories that brought it back down across the entire planet within hours. As these fragments re-entered the atmosphere at hypersonic speeds, friction heated them to incandescence. Essentially, the sky caught fire. Researchers analyzing sediment cores from the Cretaceous-Paleogene boundary find a global layer of spherules, tiny glass beads formed from molten rock droplets, mixed with soot and charcoal. This layer exists on every continent in marine and terrestrial environments, indicating that debris rained down everywhere. The thermal radiation from billions of red-hot rock fragments re-entering simultaneously created a heat pulse that may have lasted for several hours. Computer models reconstructing this thermal pulse suggest that heat flux at ground level could have reached levels equivalent to a kitchen oven set to broil, approximately 500 to 1,000 degrees F. Any organism caught in the open without shelter would have been baked or incinerated. Forests ignited across vast regions. The soot layer found at the Cretaceous-Paleogene boundary contains an estimated 15% of all above-ground biomass present on Earth at the time, suggesting that wildfires consumed roughly 70% of the world's forests. In North America, the continent closest to the impact site, The burning appears to have been nearly total. Fossil sites from Hell Creek, formation in Montana, one of the most extensively studied dinosaur-bearing formations, show an abrupt transition from diverse plant communities to fern-dominated assemblages at the boundary, a pattern consistent with recolonization of burned landscapes by opportunistic plants. Animals had nowhere to hide from the heat pulse. Large animals on land surfaces would have been killed within hours. Some researchers suggest that organisms in burrows, caves, or underwater might have survived the initial thermal pulse, which could explain why certain groups like mammals, crocodilians, and freshwater fish showed higher survival rates than large terrestrial dinosaurs. But survival of the first day meant only that organisms would face the prolonged environmental disaster that followed: sulfur dioxide and dust particles injected into the stratosphere, spread around the globe within weeks, creating an aerosol layer that reflected incoming sunlight. Photosynthesis requires light. When that light is blocked, plants die, and food chains collapse from the bottom up. Climate models simulating the aftermath of Chicxulub suggest that particulate matter and sulfate aerosols could have reduced sunlight reaching Earth's surface by 80% to 95% for several months, with partial blockage lasting for years. Surface temperatures would have dropped precipitously, perhaps by 20 to 50 degrees globally within weeks of impact. This impact winter created conditions similar to nuclear winter scenarios that concerned Cold War strategists, except far more severe and prolonged. Plants that survived the heat pulse and wildfires now faced months of near-total darkness and cold. Photosynthesis ceased or slowed to minimal levels. Terrestrial plants died back, and marine phytoplankton, the microscopic organisms that form the base of oceanic food webs, experienced massive die-offs. Evidence from marine microfossil assemblages shows that planktonic foraminifera, tiny shelled organisms that feed on phytoplankton, suffered extinction rates exceeding 90% at the boundary. When the base of the food chain collapses, everything depending on it follows. Herbivorous dinosaurs that had survived the impact day itself would have found increasingly little to eat. Carnivorous dinosaurs would have briefly benefited from abundant carcasses, but once those were consumed, prey animals vanished and starvation followed. The selectivity of extinction provides crucial clues about kill mechanisms. Non-avian dinosaurs vanished entirely, along with pterosaurs and most marine reptiles, yet birds, which are technically dinosaurs, survived, as did crocodilians, most mammal lineages, amphibians, and many fish groups. What distinguished survivors from victims? Size played a major role. Large animals require more food and are more vulnerable to disruptions in food supply. Every terrestrial animal weighing more than about 55 pounds went extinct. Smaller animals with lower metabolic demands could subsist on seeds, detritus, insects, or carcasses during the dark months and years following impact. Animals in freshwater environments showed higher survival rates than those in marine or purely terrestrial habitats, possibly because freshwater systems received nutrients from terrestrial runoff and decaying matter, supporting food chains even when photosynthesis failed. Ocean acidification struck marine ecosystems with particular severity. The massive pulse of carbon dioxide from vaporized carbonates dissolved into seawater, dropping pH levels. Organisms that build shells or skeletons from calcium carbonate, including ammonites, many species of plankton, and reef-building mollusks called rudists, face dual stresses of reduced food availability and chemically hostile water. Ammonites, those spiral-shelled cephalopods related to modern nautilus and squid, had survived for 350 million years through multiple previous extinction events. They disappeared entirely at the Cretaceous-Paleogene boundary. Rudist bivalves that had built massive reef systems across Cretaceous tropical seas also vanished, and reef ecosystems would not fully recover for millions of years. The darkness didn't lift quickly. After the initial months of near-total light blockage, atmospheric clearing occurred gradually over several years. Sulfate aerosols settled out of the stratosphere within 2 to 3 years based on atmospheric modeling. But by that point, ecosystems had been fundamentally disrupted. Surviving plants had depleted seed banks. Surviving animals faced drastically reduced populations, and ecological relationships that had structured communities for millions of years had been severed. The fossil record from the early Paleocene, the period immediately following the Cretaceous, shows ecosystems in disarray, dominated by opportunistic species rather than the complex, stable communities characteristic of the late Cretaceous. Once the skies cleared and sunlight returned, a different problem emerged. All the carbon dioxide released by vaporized carbonates and burning forests remained in the atmosphere. While sulfur aerosols cause cooling and last only a few years, carbon dioxide causes warming and persists for thousands of years. The planet shifted from impact winter to greenhouse warming. Oxygen isotope measurements from early Paleocene marine fossils indicate that ocean temperatures rose by 5 to 9 degrees within a few thousand years of the impact, a dramatic swing from the cold conditions of the impact winter. This rapid climate whiplash added further stress to ecosystems attempting to recover. The extinction wasn't quite universal, and the patterns of survival reveal important insights. In the oceans, organisms living in deep water, or those with larval stages that could remain dormant, showed higher survival rates. On land, species with generalist diets, small body sizes, and ability to shelter underground survived preferentially. Mammals, which had existed as small, largely nocturnal creatures throughout the Mesozoic, found themselves in a world suddenly emptied of the dominant predators and herbivores that had constrained their evolution for 160 million years. Within a few million years of the extinction, mammals diversified explosively, evolving into ecological roles previously occupied by dinosaurs. The discovery and confirmation of the Chicxulub impact crater represents one of geology's great detective stories. In 1980, physicist Luis Alvarez and his geologist, son Walter, published a groundbreaking paper reporting anomalously high concentrations of iridium, metal rare in Earth's crust but common in asteroids, in a clay layer, precisely at the Cretaceous-Paleogene boundary in Italy. They proposed that an asteroid impact had caused the extinction, a hypothesis that met significant skepticism from many paleontologists who favored volcanic or climate-based explanations. Throughout the 1980s, researchers found the same iridium-enriched layer at boundary sites worldwide, strengthening the impact hypothesis but raising a key question. Where was the crater? The answer came from an unexpected source. In 1991, geophysicist Alan Hildebrand and colleagues published evidence that gravity and magnetic anomalies, detected decades earlier by petroleum exploration surveys in the Yucatan, represented a massive buried impact structure. The feature's age, size, and location fit perfectly with predictions from impact models. Subsequent drilling projects retrieved shocked quartz, impact melt rocks, and other diagnostic features confirming Chicxulub as the impact site. The crater itself remains mostly buried beneath limestone sediments and offshore in the Gulf of Mexico, but geophysical surveys have mapped its distinctive multi-ring structure, characteristic of large impacts where the initial crater cavity partially collapses and rebounds, creating concentric rings of faulted and deformed rock. Not everyone accepted that the impact alone caused the extinction. Through the 1990s and 2000s, some researchers argued that massive volcanic eruptions in India, the Deccan Traps, played an equal or greater role. The timing appeared suspicious. Deccan volcanism ramped up around 66 million years ago and continued for hundreds of thousands of years, potentially releasing enormous volumes of greenhouse gases and sulfur dioxide. High-resolution dating studies have since shown that the most intense phases of Deccan eruptions occurred both before and after the impact, complicating simple cause and effect scenarios. Current scientific consensus holds that while Deccan volcanism may have stressed ecosystems and contributed to environmental instability, the Chicxulub impact delivered the fatal blow that pushed already stressed systems past critical thresholds into collapse. The impact's effects on evolution extended far beyond simply killing dinosaurs. By eliminating dominant groups, the extinction opened ecological opportunities for survivors. Mammals evolved from small, mostly insectivorous and omnivorous forms into the astonishing diversity seen in the Cenozoic. Predatory carnivores, massive herbivores, flying bats, swimming whales and seals, and eventually primates. Birds, the only surviving dinosaur lineage, diversified extensively, filling ecological roles from tiny hummingbirds to large flightless predators. In the oceans, modern fish families expanded and diversified, while new groups of marine mammals evolved from terrestrial ancestors. The world rebuilt itself, but along fundamentally different trajectories than would have occurred had the asteroid missed. The Chicxulub impact demonstrates that external, unpredictable catastrophes can reshape evolution as profoundly as gradual environmental changes or biological interactions. No amount of evolutionary adaptation could have prepared Cretaceous organisms for a mountain falling from space at 45,000 miles per hour. The randomness of the event and the arbitrary nature of which organisms happen to possess traits that allowed survival reminds us that evolutionary history contains strong elements of contingency. Had the asteroid struck a few hours earlier or later, impacting deep ocean instead of a shallow carbonate platform, sulfur release might have been far less and the extinction less severe. Had it missed Earth entirely, descendants of Tyrannosaurus and Triceratops might still roam the planet, and mammals might have remained small and marginal. While the asteroid impact at Chicxulub delivered the killing blow to the Cretaceous world, another catastrophe was already unfolding on the opposite side of the planet. In what is now west-central India, a series of volcanic eruptions had been flooding the landscape with lava for hundreds of thousands of years. The Deccan Traps, named for the Deccan Plateau they created, represent one of the largest volcanic provinces on Earth's surface. Over roughly 750,000 years spanning the end of the Cretaceous and beginning of the Paleogene, these eruptions covered approximately 200,000 square miles with layer upon layer of basaltic lava, building up deposits that in some locations exceed 1.2 miles in thickness. If the Chicxulub impact was a sudden, violent shock to Earth's systems, the Deccan Traps were a slow-motion disaster that poisoned the atmosphere and destabilized global climate for millennia. The eruptions originated from a mantle plume, a column of abnormally hot rock rising from deep within Earth's mantle toward the surface. When this plume reached the base of the lithosphere beneath the Indian subcontinent, it caused massive melting of crustal rocks. The resulting magma was basaltic, relatively low in silica, and thus fluid enough to flow great distances before solidifying. Unlike the explosive stratovolcano eruptions, familiar from places like Mount St. Helens or Krakatoa, Deccan eruptions involved long fissures opening in the crust and pouring out enormous volumes of lava that spread across the landscape like water from a broken dam. Individual lava flows extended for hundreds of miles, some covering areas exceeding 5,000 square miles, roughly the size of Connecticut, in single eruptive episodes. The volume of material erupted staggers the imagination. Estimates suggest the Deccan Traps originally covered as much as 580,000 square miles and involved the eruption of roughly 200,000 cubic miles of lava. To put that in perspective, the 1980 eruption of Mount St. Helens ejected approximately 0.25 cubic miles of material. The Deccan Traps erupted volume equivalent to 800,000 Mount St. Helens eruptions sustained over 750,000 years. Much of the original extent has been eroded away or buried beneath younger sediments, but the remaining basalt formations still cover an area larger than California and reach thicknesses that in some locations exceed 6,500 feet. The eruptions didn't occur continuously, but in distinct pulses separated by quieter intervals. Radiometric dating using argon-argon techniques on basalt samples has allowed scientists to reconstruct the eruptive chronology with increasing precision. Research published in the 2010s revealed that Deccan volcanism began approximately 66.4 million years ago, roughly 400,000 years before the Chicxulub impact. Activity continued for several 100,000 years after the impact as well. However, the dating also revealed something striking. The eruption rate, the volume of lava and gas released per unit time, increased dramatically right around the time of the impact. Some researchers propose that seismic shaking from the impact, which would have been felt globally, might have triggered increased magma flow and more vigorous eruptions, effectively linking the two catastrophes. The environmental damage from Deccan eruptions came not from lava itself, which moved slowly enough that animals could escape and affected relatively limited geographic areas at any given time, but from gases released during eruptions. When basaltic magma reaches the surface, dissolved gases bubble out of solution like carbon dioxide, escaping from an opened soda bottle. The primary gases released were sulfur dioxide, carbon dioxide, and water vapor, along with smaller amounts of hydrogen chloride and hydrogen fluoride. Estimates based on the chemistry of basalt samples and the volume erupted suggest that Deccan volcanism released between 3,000 and 9,000 gigatons of sulfur dioxide and between 15,000 and 40,000 gigatons of carbon dioxide over its active lifespan. Sulfur dioxide converts in the atmosphere to sulfate aerosols, tiny particles that reflect incoming sunlight and cause cooling. Individual eruptive pulses lasting years to decades could have injected enough sulfur into the stratosphere to drop global temperatures by several degrees for extended periods. Climate modeling suggests that during the most intense eruptive phases, global temperatures might have dropped by 7 to 9 degrees Celsius and remained suppressed for decades after major eruptions ceased. Additionally, sulfur dioxide combines with atmospheric moisture to form sulfuric acid, which falls as acid rain. The acidity of rainfall during active Deccan phases could have damaged vegetation, acidified freshwater lakes and streams, and stressed terrestrial ecosystems across large regions downwind from the volcanic sources. Carbon dioxide posed the opposite problem. While sulfur aerosols cause short-term cooling, carbon dioxide is a greenhouse gas that causes long-term warming and persists in the atmosphere for thousands of years. The Deccan eruptions released both gases simultaneously, creating a complex pattern of alternating cooling and warming cycles. During active eruptive phases with high sulfur output, global temperatures would have dropped. But as sulfur aerosols settled out of the atmosphere within a few years while carbon dioxide accumulated, temperatures would have rebounded and risen above pre-eruption levels. This climate whiplash, swings between cold and hot conditions occurring over decades to centuries, would have been extraordinarily difficult for ecosystems to handle. Species adapted to stable climatic conditions would have faced repeated stresses as temperatures oscillated. The effects extended to the oceans as well. Carbon dioxide dissolving into seawater forms carbonic acid, lowering pH and making conditions hostile for organisms that build calcium carbonate shells and skeletons. Studies of marine sediments from the final million years of the Cretaceous show evidence of multiple episodes of ocean acidification, some of which correlate with dated pulses of Deccan volcanism. These acidification events weren't as severe as what occurred during the Chicxulub impact, but they represented chronic, repeated stresses that weakened marine ecosystems. Planktonic foraminifera, microscopic shelled organisms that are sensitive indicators of ocean conditions, show declining diversity and abundance in the hundreds of thousands of years before the impact, suggesting that marine ecosystems were already under significant stress. Evidence from fossil sites in India provides direct insight into how Deccan eruptions affected local environments. Between individual lava flows, researchers find thin layers of weathered rock, soil, and sometimes fossils representing the intervals between eruptions. These intertrapian beds, as geologists call them, contain fossils of plants, freshwater mollusks, fish, amphibians, and occasional dinosaur remains. The fossil assemblages show lower diversity compared to contemporaneous sites elsewhere in the world, consistent with environments stressed by repeated volcanic disturbances. Plant fossils include species typical of disturbed early successional environments rather than mature forests. The picture that emerges is of ecosystems repeatedly reset by new lava flows and volcanic emissions, never achieving long-term stability. The debate over how much the Deccan Traps contributed to the end Cretaceous extinction has evolved as dating techniques improved. Early studies suggested that Deccan volcanism peaked either before or after the extinction boundary, which would have reduced its relevance. However, more recent high-precision uranium-lead dating of zircon crystals interbedded with Deccan lavas has refined the timeline considerably. Research published in 2015 and subsequent years showed that the largest eruptive, pulse, responsible for roughly 70% of the total Deccan lava volume, occurred in the 600,000 years straddling the Cretaceous-Paleogene boundary, with intensification right around the time of impact. This temporal overlap suggests the two events worked in concert, though the exact relationship remains debated. One hypothesis proposes that Deccan volcanism had already weakened global ecosystems by the time the asteroid struck. Species dealing with climate instability, acid rain, and ocean acidification would have had reduced resilience to withstand an additional catastrophic shock. In this scenario, the impact pushed ecosystems that were already teetering on the edge into full collapse. Support for this comes from extinction patterns in marine microfossils, which show declining diversity beginning several 100,000 years before the boundary, followed by the catastrophic final collapse at the impact horizon. An alternative view holds that Deccan emissions were significant but not severe enough alone to cause mass extinction, that the impact was the primary driver and Deccan effects were secondary or complementary. Fascinating piece of evidence linking the two events. comes from analysis of how Deccan eruption rates changed. Studies examining the structure and chemistry of lava flows immediately above and below the impact horizon find differences suggesting increased eruption rates in the post-impact period. One proposal is that seismic waves from Chicxulub, powerful enough to trigger earthquakes globally, literally shook the Deccan plume system, increasing magma flow rates and the vigor of ongoing eruptions. Computer models of seismic wave propagation show that energy from an impact the size of Chicxulub would have caused intense ground shaking on the opposite side of the planet, exactly where India was located at the time. Whether this shaking was sufficient to significantly alter volcanic activity remains an open question, but it represents an intriguing potential connection between the two disasters. The long duration of Deccan volcanism meant that, unlike the impact, which delivered a sudden, overwhelming shock, volcanic effects accumulated gradually and persisted for hundreds of thousands of years. Species couldn't simply wait out the bad conditions or rely on refuge populations to recolonize afterward. Instead, they faced an extended period of environmental instability where baseline conditions kept shifting. The fossil record shows that some groups, particularly marine organisms, declined gradually through the late Cretaceous before the final impact-related collapse, a pattern consistent with long-term stress from volcanic emissions. Rather than a single catastrophic event, the Deccan Traps also illustrate how Earth's internal dynamics can coincide with external catastrophes in ways that amplify destruction. The Indian subcontinent at 66 million years ago was positioned differently than today, located in the southern hemisphere and moving northward as the Indian tectonic plate continued its journey toward eventual collision with Asia. The mantle plume driving Deccan volcanism had been rising for millions of years before breakthrough, building pressure beneath the continental crust. When it finally breached the surface around 66.4 million years ago, the timing proved catastrophic, not because the plume knew an asteroid was coming, but because Earth systems operate on overlapping timescales where multiple processes can coincide purely by chance. Modern volcanic eruptions provide context for understanding Deccan's effects, though no historical eruption approaches its scale. The 1783-1784 Laki eruption in Iceland released approximately 15 cubic miles of basaltic lava and an estimated 120 megatons of sulfur dioxide, roughly 0.1% of the Deccan output. Yet, Laki caused measurable global cooling, crop failures across Europe and North America, and famines that killed tens of thousands of people. Extrapolating from Laki to Deccan requires multiplying effects by factors of thousands or tens of thousands, though such linear scaling likely underestimates the complexity of how Earth's climate responds to extreme forcing. The 1815 eruption of Mount Tambora in Indonesia, which caused the year without a summer in 1816, released approximately 100 times less material than a single major Deccan eruptive pulse. These historical analogues suggest that even individual Deccan eruptions would have had profound global impacts. The Deccan Traps remain visible today as stepped plateaus formed by erosion of horizontal lava flows. The Western Ghats mountain range in India exposes spectacular sections through the flood basalts, where individual flows can be traced laterally for dozens of miles. Geologists studying these formations find evidence of at least 30 to 35 major eruptive episodes, each producing flows that covered thousands of square miles. The chemical composition of individual flows varies slightly, indicating that different batches of magma, drawn from different depths or having experienced different degrees of crystallization, fed successive eruptions. This chemical stratigraphy allows correlation of lava flows across the entire Deccan province and helps reconstruct the sequence and timing of eruptive activity. Beyond their role in the extinction, the Deccan Traps provide insight into how large igneous provinces form and what triggers them. Mantle plumes, the deep-seated columns of hot rock that drive flood basalt volcanism, remain somewhat mysterious. Scientists can observe their surface manifestations but cannot directly sample the deep mantle where they originate. The Deccan plume is thought to have originated at the core mantle boundary, nearly 1,800 miles beneath the surface, and taken tens of millions of years to rise through the mantle. Why plumes form in the first place, why they occur where they do, and what controls their timing remain active areas of research. Some scientists propose that plumes initiate at the boundaries of large, low shear velocity provinces, mysterious, structures at the base of the mantle detected by seismic waves, but confirming such hypotheses requires continued study of both modern and ancient large igneous provinces. The Deccan eruptions represent an enduring lesson about how internal Earth processes can dramatically alter surface environments. While we tend to think of Earth's interior and surface as separate realms, they're intimately connected through volcanism. Gases that spent millions of years locked in minerals deep underground can be rapidly transferred to the atmosphere during eruptive episodes, altering climate on timescales of years to millennia. The carbon dioxide released by Deccan volcanism originated partly from melting of carbonate rocks in the crust and partly from the mantle itself. Carbon that had been cycled into Earth's interior through subduction of oceanic plates and stored for hundreds of millions of years. When eruptions release this stored carbon, they short-circuit the normal, slow pace of the geological carbon cycle. The coincidence of Chicxulub impact and Deccan volcanism, two rare, catastrophic events occurring within hundreds of thousands of years of each other, raises questions about probability and contingency in Earth's history. Were ecosystems simply unlucky to face both disasters simultaneously, or does some deeper connection exist? While the seismic triggering hypothesis provides one possible link, the broader question remains open. What we can say with certainty is that the combination of prolonged volcanic stress and sudden impact shock created conditions that overwhelmed the resilience of Cretaceous ecosystems, ending one of Earth's most successful evolutionary experiments and opening the door to the world we recognize today. 445 million years ago, Earth's oceans teemed with life unlike anything in modern seas. No fish yet swam these waters. Instead, bizarre arthropods called trilobites crawled across seafloors in countless forms, from species smaller than a fingernail to giants exceeding 2 feet in length. Nautiloid cephalopods, some with straight conical shells reaching 20 feet long, patrolled as apex predators. Coral-like organisms called tabulate and rugose corals built extensive reef structures in warm, shallow seas, while crinoids, filter-feeding relatives of starfish and sea urchins, waved their feathery arms in the currents. Brachiopods, superficially resembling clams but actually unrelated, dominated seafloor communities by sheer abundance and diversity. On land, vegetation had barely begun to colonize terrestrial environments. Perhaps some primitive mosses and liverworts clung to moist rocks near water, but forests, grasslands, and soil ecosystems lay tens of millions of years in the future. Life remained overwhelmingly marine, and the Ordovician oceans represented one of the most biologically rich periods in Earth's history. Then ice came, and within a geologically brief interval, 85% of all species vanished in what would become known as the late Ordovician mass extinction. The Ordovician period, spanning from 485 to 443 million years ago, was characterized by warm global temperatures and high sea levels. Shallow continental seas flooded vast areas of the continents, creating extensive epicontinental seaways, bodies of marine water covering what would normally be dry land. These shallow, sunlit environments provided ideal habitat for marine life, and diversity exploded. Paleontologists estimate that marine invertebrate diversity tripled during the Ordovician, reaching levels that wouldn't be surpassed until much later in Earth's history. Most continents at this time were clustered in the southern hemisphere or straddling the equator. The massive supercontinent Gondwana, which included what would become South America, Africa, Antarctica, Australia, and India, dominated the southern latitudes, but was positioned with its center near the equator and its margins extending into temperate zones. Then Gondwana began to drift. Driven by plate tectonics, this massive landmass moved southward, gradually positioning itself over the South Pole. The reasons behind this particular plate motion remain debated. Plate movements result from complex interactions of mantle convection, subduction zones pulling oceanic plates downward, and the push of mid-ocean ridges. Whatever the specific drivers, by approximately 445 million years ago, Gondwana had moved sufficiently far south that a significant portion of the supercontinent lay over polar latitudes. When large landmasses position themselves over the poles, they create conditions favorable for glaciation. Land surfaces reflect more sunlight than open ocean, and continents provide elevated areas where snow can accumulate year-round. Once ice sheets begin forming, they create positive feedback loops. White ice reflects even more sunlight, cooling the region further and allowing ice to spread. Geological evidence from rocks in north, Africa and South America, regions that were part of Gondwana and located near the South Pole during the late Ordovician, preserves distinctive signs of glaciation. Geologists find glacial till deposits, unsorted mixtures of rock fragments ranging from fine clay to house-sized boulders, created when glaciers grind across landscapes and deposit debris. They find striated bedrock surfaces, scratched and polished by rocks embedded in the base of moving ice sheets. They find dropstones in marine sediments, isolated boulders that fell from melting icebergs into seafloor muds, creating structures impossible to explain by any process other than glacial ice rafting. These features occur in formations dated to 445 million years ago and indicate that extensive ice sheets, probably comparable in size to the modern Antarctic ice sheet, developed over portions of Gondwana. As glaciers grew, they locked up enormous quantities of water that had previously been in the oceans. Sea level dropped in response. Estimates, based on the extent of glaciation and analysis of coastal sediment patterns, suggest sea level fell by approximately 330 feet during the maximum extent of late Ordovician glaciation. To put that in perspective, if all ice on modern Earth melted, sea level would rise by about 230 feet. The late Ordovician glaciation involved ice sheets larger than those present today. For marine organisms adapted to shallow epicontinental seas, this sea level drop was catastrophic. Vast areas of seafloor that had been productive habitat suddenly became exposed land. The continental shelves drained, eliminating environments that supported the majority of marine biodiversity. The extinction didn't happen all at once. High-resolution stratigraphic studies of fossil-bearing formations from this interval reveal two distinct pulses of extinction separated by roughly 500,000 to 1 million years. The first pulse, occurring at the boundary between the Cattian and Hernantian stages approximately 445 million years ago, coincided with the onset of rapid glaciation and sea level drop. Tropical and subtropical species adapted to warm, stable, shallow seas suffered most severely during this phase. Graptolites, colonial organisms that floated in open water and are important index fossils for this period, experienced major losses. Brachiopod diversity plummeted as their preferred shallow water habitats disappeared. Trilobite families that had thrived for millions of years vanished entirely. Ocean temperatures dropped significantly as glaciation intensified. Oxygen isotope measurements from fossil shells provide a proxy for ancient temperatures. The ratio of oxygen 18 to oxygen 16 in calcium carbonate shells changes predictably with the temperature of the water in which the organism lived. Analysis of late Ordovician fossils indicates that tropical sea surface temperatures fell by approximately 9 to 11 degrees during the glacial maximum, while deeper waters and higher latitudes cooled even more dramatically. For species with narrow thermal tolerances, this cooling alone would have been lethal. Additionally, colder water holds more dissolved oxygen, and the increase in oxygenation would have altered marine chemistry in ways that affected organisms adapted to warmer, lower oxygen conditions. The second extinction pulse occurred roughly 500,000 years later, at the end of the Hernantian stage, around 443 million years ago. Paradoxically, this pulse appears to have been triggered by the opposite condition: rapid deglaciation. Climate models and geological evidence suggest that glaciation was relatively short-lived by geological standards, lasting perhaps 1 to 2 million years at most. As ice sheets melted, sea levels rose rapidly, reflooding the continental shelves. Species that had survived the first pulse by adapting to deeper, cooler waters or by migrating to refuge areas now faced a different set of challenges. Rising seas brought warmer temperatures, reduced oxygen concentrations, and disrupted ocean circulation patterns. Species that had adapted to the glacial conditions couldn't readapt quickly enough when conditions reversed. The rapidity of these environmental swings appears crucial to understanding extinction severity. If climate had shifted slowly over tens of millions of years, species might have tracked their preferred environments by migrating, or populations might have evolved adaptations to new conditions. But the late Ordovician changes occurred over timescales of hundreds of thousands of years, far faster than most species could adapt through evolution, yet not quite fast enough for migration to be a reliable survival strategy, given the complete drainage and reflooding of entire sea basins. Species found themselves in an evolutionary trap, caught between conditions changing too fast to adapt to. but occurring over timescales long enough that simply enduring bad conditions wasn't viable. What triggered the initial glaciation remains debated. One hypothesis involves the rise of the Appalachian Mountains. Continental collisions during the Ordovician created this mountain range, and the resulting uplift exposed vast areas of fresh rock to weathering. Chemical weathering of silicate rocks consumes atmospheric carbon dioxide. Rainwater combines with CO2 to form carbonic acid, which reacts with minerals in rocks, ultimately locking carbon in carbonate minerals that wash into the ocean and settle as seafloor sediments. Increased weathering rates from Appalachian uplift could have drawn down atmospheric CO2 concentrations sufficiently to tip Earth into glaciation, especially once Gondwana had drifted over the South Pole where ice could nucleate. Another contributing factor may have been the evolution of land plants. The late Ordovicians saw the first significant colonization of terrestrial environments by primitive plants. While these weren't forests, likely just low-growing, mosses and simple vascular plants in wetland areas, even limited plant cover would have increased weathering rates by stabilizing soils and keeping rock surfaces moist. Plant roots also secrete organic acids that enhance mineral breakdown. Early plants may have accelerated CO2 drawdown beyond what mountain building alone could achieve. Additionally, as plant debris accumulated and became buried in sediments, it sequestered carbon that would otherwise have returned to the atmosphere through decomposition, creating another mechanism for reducing atmospheric CO2. The selectivity of extinction provides insights into kill mechanisms. Tropical species suffered more severely than those from higher latitudes. Organisms already adapted to cooler conditions had less distance to move to find suitable habitat as the planet cooled. Generalist species with wide environmental tolerances survived better than specialists. Free-swimming organisms showed higher survival rates than those attached to seafloors, possibly because mobile species could migrate to follow suitable conditions while sessile species were trapped in place as their environment became uninhabitable. Deep water species survived somewhat better than shallow water forms, consistent with sea level drop eliminating shallow habitats while deeper waters persisted. Recovery from the late Ordovician extinction took several million years. Unlike some mass extinctions where opportunistic species rapidly fill vacant ecological niches, the post-Ordovician oceans show a prolonged period of low diversity and simplified ecosystems. Reef systems built by corals and other calcifying organisms were essentially absent for the first 5 million years of the Silurian period that followed. Brachiopod communities that had been extraordinarily diverse, with dozens of species coexisting in single locations, were replaced by impoverished assemblages containing only a handful of species. The structure of marine food webs simplified dramatically, with fewer trophic levels and less specialization among surviving species. Why did recovery take so long? Part of the answer lies in the severity of habitat loss. The draining of epicontinental seas eliminated not just organisms, but the physical environments they inhabited. When seas reflooded continental shelves during deglaciation, the environments that returned weren't identical to those that had been lost. Sediment patterns had changed, water chemistry differed, and the communities that had structured these habitats for millions of years were gone. Recolonization occurred slowly, starting from surviving populations in deeper waters or from refugia in regions less severely affected by climate swings. Additionally, with so few species surviving, the raw material for evolutionary diversification had been depleted. Generating new species through evolution requires existing populations to diverge. When most populations have been eliminated, the process simply takes longer. The late Ordovician extinction demonstrates that rapid climate change, even without asteroids or massive volcanic eruptions, can drive severe mass extinction. The trigger was ultimately tectonic, the drift of Gondwana over the South Pole, but the kill mechanisms were environmental: temperature change, sea level fluctuation, and habitat loss. This makes the event particularly relevant for understanding how climate systems interact with biology. Species don't exist in isolation from their physical environment. They're adapted to specific temperature ranges, salinity levels, oxygen concentrations, and habitat structures. When those parameters shift beyond tolerance limits faster than evolution or migration can compensate, extinction follows. The event also reveals the dangers of climate whiplash. Both cooling and warming caused extinctions, suggesting that the direction of change matters less than its speed and magnitude. Ecosystems have some resilience to environmental variation. seasonal changes, short-term weather fluctuations, even gradual shifts over thousands of years can often be absorbed without catastrophic losses. But when conditions swing rapidly between extremes, as happened during the late Ordovician with glaciation followed by deglaciation, even resilient ecosystems break. Species that adapt to cold conditions become vulnerable when warming returns, and vice versa. There's no stable target to adapt toward, only moving goalposts that shift faster than natural. Selection can track. One of the more sobering aspects of the late Ordovician extinction is its demonstration. The Earth's climate can shift into glaciation surprisingly quickly when conditions align. The planet was warm, no permanent ice sheets existed anywhere, and then within perhaps a few 100,000 years, massive glaciers covered millions of square miles. Once ice sheets nucleate, positive feedbacks accelerate their growth. Ice reflects sunlight, cooling the region further. Cooler air holds less moisture, reducing snowfall, but also reducing melting, allowing ice to accumulate. As ice sheets grow and cool the planet, atmospheric CO2 dissolves more readily into cold ocean water, removing greenhouse gas and allowing further cooling. These feedbacks can drive climate across tipping points into new stable states that persist for millions of years. The Ordovician glaciation eventually ended, but the mechanisms of deglaciation remain less clear than those of ice sheet initiation. Volcanic outgassing continuously adds CO2 to the atmosphere, and with reduced weathering rates on ice-covered continents, CO2 would have gradually accumulated until greenhouse warming overcame the ice albedo feedback. But the rapidity of deglaciation, suggested by geological evidence, indicates this wasn't a simple, gradual process. Some researchers propose that once melting begins and ice sheets start retreating, positive feedbacks again take over. Darker land and ocean surfaces absorb more heat, accelerating melting, which exposes more dark surface, creating a runaway deglaciation. The same feedback mechanisms that made glaciation self-reinforcing worked in reverse during ice retreat. The late Ordovician mass extinction stands as the first of Earth's big 5 mass extinctions, those events severe enough to fundamentally reshape the trajectory of evolution. It occurred early in the history of complex animal life, eliminating many experimental body plans and ecological strategies that had emerged during the Cambrian explosion of biodiversity 50 million years earlier. The species that survived and subsequently diversified weren't necessarily superior in any absolute sense, but they happened to possess traits, thermal tolerance, broad dietary preferences, mobile lifestyles, that proved advantageous under the specific conditions of late Ordovician climate chaos. Evolution is contingent, and this extinction reinforced that contingency, pruning the tree of life in ways that determined which lineages would dominate future oceans and eventually give rise to fish, land vertebrates, and ultimately humans. 201 million years ago, the supercontinent Pangaea began to fracture. What would eventually become the Atlantic Ocean started as a series of massive rifts splitting apart the joined landmasses of Africa and South America from North America and Europe. This wasn't a quiet, gradual separation. As continental crust stretched and thinned, magma from Earth's mantle welled up through enormous fissures, triggering one of the most voluminous volcanic episodes in the planet's history. The Central Atlantic Magmatic Province, CAMP, as geologists abbreviate it, would eventually cover more than 4 million square miles across 4 continents with flood basalts and intrusive rocks. The eruptions coincided precisely with the end of the Triassic period and the beginning of the Jurassic, and with them came an extinction event that eliminated approximately 76% of all species on Earth. This wasn't the most severe of the mass extinctions. That distinction belongs to the Permian Triassic event, but it ranks among the Big Five and fundamentally restructured terrestrial and marine ecosystems, ultimately allowing dinosaurs to rise from relative obscurity to dominance. The Triassic period had been a time of recovery and experimentation following the devastation of the Great Dying. Ecosystems had spent tens of millions of years rebuilding complexity after that earlier catastrophe. By the late Triassic, diverse communities of reptiles filled ecological roles on land. Dinosaurs existed, but they remained relatively small and ecologically marginal compared to other groups. The dominant large herbivores were rhynchosaurs, beaked reptiles that used their specialized jaws to process tough vegetation. Large predators included rauisuchians, crocodile relatives that walked upright on their hind legs and reached lengths exceeding 20 feet. Dicynodonts, mammal-like reptiles that had survived the Permian extinction, still persisted in some environments. Early mammals scurried through underbrush as small nocturnal insectivores. In the oceans, marine reptiles including ichthyosaurs and early plesiosaurs patrolled as top predators. Coral reefs had finally recovered from the Permian devastation and once again flourished in shallow tropical seas. Then came the rifting. As Pangaea split, magma didn't erupt from traditional cone-shaped volcanoes, but from vast fissures opening in the crust as continents pulled apart. Imagine cracks in the Earth's surface hundreds of miles long, pouring out fluid basaltic lava that flowed across landscapes and accumulated in layers. The volume of magma erupted is staggering. Estimates suggest at least 1 million cubic miles of lava and associated intrusive rocks formed during the main pulse of camp activity. These eruptions occurred across what is now eastern North America, northwestern Africa, southwestern Europe, and northeastern South America, regions that were joined together as part of Pangaea but have since drifted thousands of miles apart. Finding chemically identical basalts on opposite sides of the Atlantic Ocean provided some of the key evidence supporting plate tectonic theory in the 20th century. High-precision radiometric dating has pinned the timing of camp eruptions to an extraordinarily narrow window. Uranium lead dating of zircon crystals from volcanic rocks gives ages of 201.5 million years, with uncertainties of only about 20,000 years, remarkably precise for events so ancient. This age matches exactly with the Triassic Jurassic boundary identified in fossil-bearing sedimentary rocks worldwide. The coincidence is too precise to be accidental. Camp volcanism caused the extinction. But how did volcanic eruptions concentrated in one region of Pangaea kill 3/4 of all species globally? The primary kill mechanism was atmospheric poisoning from volcanic gases. When basaltic magma rises through continental crust, it doesn't just release gases dissolved in the magma itself. The intense heat bakes surrounding rocks, releasing additional gases from sediments the magma passes through. Camp magmas intruded through sedimentary basins containing organic-rich rocks, essentially coal and oil deposits, and evaporate deposits containing sulfur compounds. Conservative estimates suggest camp eruptions released approximately 20,000 to 30,000 gigatons of carbon dioxide and comparable amounts of sulfur dioxide over roughly 600,000 years. However, the eruptions weren't continuous. Evidence from the structure and chemistry of lava flows indicates that volcanic activity occurred in distinct pulses, each lasting perhaps tens of thousands of years, separated by quieter intervals. Carbon isotope measurements from marine and terrestrial rocks spanning the Triassic-Jurassic boundary reveal multiple rapid excursions, sharp changes in the ratio of carbon-13 to carbon-12 that indicate massive injections of isotopically light carbon into the atmosphere-ocean system. These excursions correspond to pulses of extinction visible in the fossil record. The pattern suggests that volcanic episodes released pulses of carbon dioxide, each causing environmental disruption and species losses, with partial recovery during quiet intervals. Before the next pulse struck, atmospheric carbon dioxide concentrations likely climbed to levels exceeding 2,000 parts per million, more than 5 times pre-industrial levels and double current concentrations. Climate models simulating these conditions indicate that global average temperatures rose by approximately 9 to 14 degrees during the most intense phases of volcanic activity. Tropical regions already warm became dangerously hot. Evidence from fossil leaf assemblages shows that plant communities in equatorial and low-latitude regions underwent dramatic compositional changes at the Triassic-Jurassic boundary, with heat-tolerant species replacing those adapted to slightly cooler conditions. Some paleobotanists estimate that summer temperatures in tropical lowlands may have exceeded 122 to more, beyond the thermal tolerance limits for most land vertebrates. The warming wasn't uniform. Continental interiors experienced more extreme temperature increases than coastal regions, creating vast zones in the heart of Pangaea that became essentially uninhabitable during the hottest phases. This is particularly significant because Pangaea's enormous size meant that much of its land area lay far from moderating oceanic influences. Even under normal conditions, Pangaean interiors experienced severe seasonal temperature extremes and arid conditions, adding 10 to 15 degrees of greenhouse warming on top of already extreme baseline temperatures pushed these regions beyond habitability. Thresholds for many organisms. Ocean acidification struck marine ecosystems with devastating effect. Carbon dioxide dissolving into seawater forms carbonic acid, and the massive CO2 pulses from camp volcanism dropped ocean pH significantly. Reef-building corals suffered catastrophic losses. Fossil evidence shows that coral reefs essentially disappeared at the Triassic-Jurassic boundary and wouldn't fully recover for millions of years. Other calcifying organisms, including many mollusks, brachiopods, and planktonic species with calcium carbonate shells, also experienced severe extinction. The fossil record shows a dramatic decline in the abundance of thick-shelled organisms, replaced temporarily by species with thinner shells or no shells at all, organisms less affected by acidified waters. Marine reptiles experienced mixed fates. Some ichthyosaur groups disappeared, while others survived and would go on to dominate Jurassic oceans. Placodonts, specialized marine reptiles that fed on hard-shelled invertebrates, vanished entirely. Their extinction likely linked to the collapse of reef ecosystems and shellfish populations that formed their primary food source. Ammonoids, already reduced by the earlier Permian extinction, suffered another severe blow. With all but one or two lineages going extinct, the survivors would subsequently diversify during the Jurassic, filling oceans with the spectacular variety of ammonite forms familiar from fossil collections, only to face final extinction 135 million years later. On land, the extinction reshaped terrestrial vertebrate communities fundamentally. Large-bodied herbivores and carnivores suffered disproportionately. Decinodonts, which had survived from the Permian through the entire Triassic, finally vanished. Rauisuchians disappeared completely, along with most other archosaur groups that had dominated late Triassic ecosystems. Rhynchosaurs went extinct. Atosaurs, armored pig-like reptiles that had been abundant herbivores, vanished. The pattern suggests that disruption of plant communities at the base of terrestrial food chains created cascading extinctions up through herbivores and then carnivores. Large animals with high metabolic demands and lengthy generation times couldn't adapt quickly enough to changing food availability. Dinosaurs survived and subsequently diversified into the dominant, large land animals of the Jurassic and Cretaceous. Why did they survive when so many other archosaur lineages perished? The answer isn't entirely clear, but late Triassic dinosaurs were generally smaller than competing archosaurs and occupied somewhat different ecological niches. Many early dinosaurs appear to have been bipedal, potentially more mobile and better able to range widely in search of resources during environmental instability. Some researchers propose that dinosaurs possessed more efficient respiratory systems or thermoregulatory capabilities that gave them advantages under high CO2, high temperature conditions, though evidence for such physiological differences remains debated. Mammals also survived, though they remained small and nocturnal throughout the subsequent Jurassic period. Their survival likely relates to small body size, low metabolic demands, and nocturnal habits that allowed them to avoid the most extreme daytime temperatures. Burrowing behaviors would have provided refuge from heat and potentially from wildfires that evidence suggests became more frequent during camp volcanic pulses. Plant communities show elevated charcoal abundances at the Triassic-Jurassic boundary, indicating increased fire activity, likely a consequence of both lightning strikes in a more CO2-rich atmosphere and vegetation stressed by heat and possibly drought becoming more flammable. The fossil record reveals that the extinction occurred in multiple phases rather than a single, catastrophic moment. Marine sections in northwestern Europe and western North America show at least 3 distinct episodes of faunal turnover, separated by intervals of relative stability lasting tens of thousands of years. Each episode corresponds to carbon isotope excursions indicating massive CO2 release, suggesting that successive volcanic pulses drove successive extinction waves. Species that survived the first pulse faced renewed stress during subsequent episodes, and even organisms that had temporarily adapted to the new conditions were pushed to extinction by repeated environmental shocks. Ocean circulation patterns appear to have been disrupted as well. Warming reduces the density difference between polar and equatorial waters, weakening the thermohaline circulation that mixes oxygen-rich surface waters into the deep ocean. Sedimentary rocks from the Triassic-Jurassic boundary interval show geochemical signatures indicating reduced oxygenation in deeper marine environments, not as severe as the anoxia during the Permian extinction, but significant enough to stress deep water communities. Some marine basins appear to have developed stratified water columns where a warm, less dense surface layer prevented mixing with cooler, deeper waters. creating oxygen-depleted zones that eliminated seafloor organisms. The recovery from the Triassic Jurassic extinction followed a pattern similar to other major extinctions, a prolonged interval of low diversity and ecological simplification followed by gradual rebuilding of complexity. Jurassic ecosystems that emerged several million years after the extinction boundary looked fundamentally different from late Triassic ones. Dinosaurs dominated terrestrial megafauna roles previously held by diverse archosaur groups. Marine reptiles diversified into new forms. Reef ecosystems eventually recovered, but were built by different coral groups than those that had dominated the Triassic. The extinction acted as a reset button, eliminating established ecological structures and allowing surviving lineages to radiate into vacant niches. The Triassic-Jurassic extinction demonstrates again the vulnerability of Earth's biosphere to rapid carbon injection and climate warming. The kill mechanisms, heat stress, ocean acidification, oxygen depletion, mirror those identified in other extinction events driven by volcanism. A pattern emerges across these catastrophes. When carbon dioxide enters the atmosphere faster than natural weathering processes can remove it, greenhouse warming accelerates beyond the pace at which species can adapt or migrate. Modern climate concerns about anthropogenic carbon emissions draw uncomfortable parallels to these ancient volcanic events, though the rate of current emissions actually exceeds volcanic emission rates from most flood basalt provinces. Camp volcanism also illustrates how plate tectonics shapes the history of life. The breakup of Pangaea wasn't just a geological event, reshuffling continental positions. It was a biological catastrophe that killed 3/4 of existing species and determined which lineages would dominate the next 135 million years. Had camp eruptions been less severe, or had they occurred at a different time or in a different geological setting, dinosaurs might have remained marginal players and some other archosaur group might have risen to dominance. The contingency of evolution becomes starkly apparent. Outcomes depend not just on competitive abilities or adaptive traits, but on random geological events that restructure the playing field. The Triassic-Jurassic boundary also marks a transition in Earth's climate state. The Triassic had been hot and relatively arid, with strong seasonal contrasts and vast desert belts in Pangaea's interior. The Jurassic would be warmer still, but with more humid conditions and higher sea levels as the fragmenting continents created more coastal environments. Camp volcanism contributed to this shift, not just through its immediate effects, but through long-term consequences of continental rifting. As the Atlantic Ocean opened, new patterns of ocean circulation emerged, redistributing heat around the planet and creating climate zones different from those that had existed when continents were joined. One fascinating aspect of the Triassic-Jurassic extinction is how visible it remains in the modern landscape. Camp basalts outcrop prominently along the eastern coast of North America as the Palisades along the Hudson River, in the Connecticut River Valley as the cliffs of East Rock and West Rock, and across the Appalachian region as diabase intrusions. These rocks, cooled from magma 201 million years ago during one of Earth's great catastrophes, now form scenic viewpoints and recreational areas. Walking across these ancient lava flows connects us directly to an event that reshaped the trajectory of evolution and set the stage for the age of dinosaurs. The extinction eliminated competitors and opened ecological space. Dinosaurs walked through that space and came to dominate terrestrial ecosystems for the next 135 million years, until another catastrophe, an asteroid strike, would end their reign and open new opportunities for mammals. 375 million years ago, Earth's oceans were dying from the inside out. Unlike the sudden catastrophes of asteroid impacts or the dramatic surges of volcanic eruptions, this extinction unfolded slowly, occurring in pulses spread across 25 million years during the late Devonian period. By the time it concluded around 359 million years ago, approximately 75% of all species had vanished. The cause wasn't fire or ice, impact or eruption, but something more insidious. The oceans were running out of oxygen, vast zones of anoxic water, dead zones where dissolved oxygen concentrations dropped to levels unable to support most animal life, spread across sea floors and even into shallow waters. Marine organisms suffocated en masse, repeatedly, in extinction pulses that struck every few million years. The late Devonian extinctions represent one of the longest and most complex mass extinction events in Earth's history. and their primary cause came not from volcanic gases or extraterrestrial impacts, but from life itself. The Devonian period, spanning from 419 to 359 million years ago, witnessed revolutionary changes in terrestrial ecosystems. This was the time when plants truly conquered the land. Early Devonian vegetation consisted of small, primitive vascular plants barely reaching knee height. By the late Devonian, true forests had emerged. Massive trees like Archaeopteris grew to heights exceeding 100 feet, spreading across floodplains and creating the first complex forest ecosystems. These weren't modern trees, but rather tree ferns and early seed plants with fundamentally different anatomies. Their evolution represented one of the most important ecological transitions in Earth's history, but it came with catastrophic, unintended consequences for marine life. As forests spread, they fundamentally altered how nutrients moved from land to sea. Plant roots broke down rock and stabilized soil, but they also accelerated weathering processes. When plants died, their organic matter accumulated in thick deposits. Rainfall washed nutrients, particularly nitrogen and phosphorus, from soils and decaying vegetation into rivers, which carried them to the oceans. This nutrient runoff fertilized coastal waters, triggering explosive blooms of algae and cyanobacteria. While this might sound beneficial, adding nutrients to food webs, the consequences were deadly. When algal blooms die, they sink to the seafloor where bacteria decompose them. Bacterial decomposition consumes oxygen. When nutrient inputs are modest, oxygen consumption remains balanced by mixing of oxygen-rich surface waters downward. But when nutrients flood in from continents covered by newly evolved forests, algal blooms become so massive that their decay overwhelms oxygen supply. Geological evidence for these ancient dead zones comes from distinctive black shale deposits found in late Devonian rocks worldwide. Black shales form when organic-rich sediments accumulate in oxygen-depleted waters. Normally, bacteria and scavenging organisms on the seafloor consume dead organic matter, recycling nutrients and preventing massive organic accumulation. But when oxygen drops below critical thresholds, these decomposers can't survive, and organic matter accumulates and becomes buried in sediments. The black color comes from unoxidized organic carbon and iron sulfide minerals that form only in anoxic conditions. Late Devonian black shales occur in formations across North America, Europe, and North Africa, regions that occupied different positions and climatic zones during the Devonian, indicating that anoxia was a global phenomenon, not a localized problem. Chemical analysis of these black shales provides additional evidence of oxygen depletion. Trace metals like molybdenum and uranium accumulate in anoxic sediments in concentrations far exceeding those found in well-oxygenated environments. Biomarker molecules, distinctive organic compounds produced by specific types of organisms, preserved in Devonian black shales include isoraneratane, a compound synthesized only by green sulfur bacteria. These bacteria thrive in anoxic water containing hydrogen sulfide and require light for photosynthesis, meaning they live in shallow waters or the photic zone of stratified water columns. Finding their biomarkers in late Devonian rocks indicates that anoxia wasn't confined to deep basins but extended into shallow waters where light penetrated, conditions that would have been toxic to most marine animals. The extinction didn't strike all organisms equally. Reef-building organisms suffered catastrophically. Devonian reefs were constructed primarily by stromatoporoid sponges and tabulate and rugose corals, creating massive structures comparable in scale to modern coral reefs. These organisms require well-oxygenated water and cannot survive prolonged anoxia. At the Kelwasser event, the first major extinction pulse around 375 million years ago, reef ecosystems collapsed across the globe. When geologists trace fossil reefs through late Devonian rock formations, they find an abrupt boundary where diverse, thriving reef communities disappear and are replaced by barren sediments or simple microbial mats. Reefs wouldn't fully recover until tens of millions of years later in the Carboniferous period. Trilobites, those iconic arthropods that had dominated seafloors for over 200 million years, suffered severe losses during the late Devonian. Dozens of trilobite families that had been abundant in Middle Devonian seas disappeared during the extinction pulses. Placoderms, armored fish that were the dominant vertebrate predators of Devonian oceans, experienced devastating declines. These fish, which included the massive Dunkleosteus with jaws powerful enough to bite through bone and armor, had radiated into hundreds of species occupying ecological roles from small bottom feeders to apex predators. The late Devonian extinctions eliminated most placoderm diversity, and the group would vanish entirely by the end of the Devonian. Their ecological roles as large predators would be inherited by early sharks and bony fish, which showed higher survival rates during the anoxic crises. The extinction occurred in at least 2 major pulses, possibly more depending on how paleontologists define boundaries. The Kellwasser event, named for limestone formations in Germany where it was first identified, occurred approximately 375 million years ago, near the boundary between the Frasnian and Furmenian stages of the late Devonian. High-resolution analysis of fossil assemblages shows that this event actually consisted of 2 closely spaced extinction pulses separated by perhaps 500,000 years, the lower and upper Kellwasser events. Each pulse corresponds to deposition of black shales and dramatic drops in fossil diversity. The second major pulse, called the Hangenberg event, occurred at the very end of the Devonian around 359 million years ago, marking the boundary with the subsequent Carboniferous period. Ocean stratification appears to have played a crucial role in creating and sustaining anoxic conditions. When surface waters warm significantly, either from greenhouse warming or changes in ocean circulation, the density difference between warm surface layers and cooler deep waters increases. This stratification prevents mixing of oxygen-rich surface waters downward into deeper layers. Without replenishment from above, oxygen in deep waters becomes depleted as organisms consume it through respiration, and bacteria consume it through decomposition of organic matter. Once stratification establishes, it becomes self-reinforcing. The boundary between oxygenated surface water and anoxic deep water, called a chemocline, persists and can even migrate upward toward the surface as anoxic conditions worsen. Climate played a complicating role. The late Devonian experienced significant climate fluctuations, with periods of warming and cooling that appear to correlate with extinction pulses. Sea level changes, rising and falling by hundreds of feet, occurred repeatedly throughout the late Devonian, each fluctuation disrupting coastal and shelf environments. When sea level rose, flooding continental margins, it created vast areas of shallow seas, perfect for nutrient accumulation and algal blooms. When sea level dropped, these areas drained, potentially releasing nutrients from exposed sediments during subsequent reflooding. This created a pump mechanism that could have injected massive nutrient pulses into marine environments repeatedly. Volcanic activity may have contributed as well, though its role remains less clear than in other mass extinctions. Some researchers point to increased volcanic activity during the late Devonian, with eruptions potentially releasing carbon dioxide that warmed climate and acidified oceans. However, no volcanic province comparable to the Siberian Traps or Deccan Traps has been identified for this time period. The volcanism that did occur appears modest compared to that associated with other major extinctions. This suggests that while volcanism may have been a contributing factor, the primary driver was the nutrient overload from terrestrial plant evolution overwhelming marine ecosystems. Ironically, the expansion of forests that contributed to marine extinctions also transformed terrestrial environments in ways that would eventually benefit life. Deep soils formed for the first time as plant roots broke down rock and organic matter accumulated. These soils retained moisture, allowing plants to colonize previously uninhabitable areas and creating habitats for the first terrestrial arthropods and vertebrates to venture far from water sources. Insects evolved and diversified in Devonian forests, with some species developing wings by the end of the period, the first animals to master powered flight. Tetrapods, 4-legged vertebrates that were ancestors of all land vertebrates, including humans, evolved during the Devonian from lobe-finned fish. While marine ecosystems suffered repeated anoxic crises, life on land was undergoing revolutionary expansion. The organisms that survived the late Devonian extinctions weren't randomly selected. Fish that could tolerate low oxygen conditions, species with efficient respiratory systems or ability to gulp air at the surface, survived better than those requiring high oxygen concentrations. Bottom-dwelling organisms that could burrow into sediments or migrate vertically in the water column to find oxygenated zones showed higher survival rates than sessile species rooted to the seafloor. Organisms in well-mixed coastal environments or in fresh water, systems fed by well-oxygenated River flows survive better than those in stagnant basins or stratified offshore waters. The duration of the late Devonian extinctions, 25 million years from first pulse to final collapse, raises questions about why ecosystems never fully recovered between crisis episodes. Part of the answer lies in positive feedbacks. Once anoxic conditions develop and eliminate oxygen-dependent seafloor communities, the biological mechanisms that normally consume organic matter before it accumulates fail. More organic matter buries, releasing nutrients during subsequent decomposition, feeding more algal blooms, consuming more oxygen, expanding anoxic zones further. Breaking this cycle requires fundamental changes to nutrient inputs or ocean circulation changes that apparently didn't occur until forest expansion reached an equilibrium. And weathering rates stabilized, modern oceans experience similar phenomena. Coastal dead zones form in the Gulf of Mexico, Baltic Sea, and off major river deltas worldwide where agricultural runoff carries excess nitrogen and phosphorus into marine waters. These contemporary dead zones provide alarming parallels to late Devonian conditions. Algal blooms fed by fertilizer runoff die and decompose, consuming oxygen and creating zones where fish and bottom-dwelling organisms cannot survive. The Gulf of Mexico dead zone can exceed 8,000 square miles during summer months, larger than New Jersey. While modern dead zones are typically seasonal and reversible when nutrient inputs decrease, they demonstrate how quickly marine ecosystems can flip from oxygen-rich to oxygen-depleted states when nutrient loading exceeds critical thresholds. The late Devonian extinctions reveal that biological innovations can have catastrophic unintended consequences. Forest evolution represented one of the most important advances in the history of life, enabling terrestrial ecosystems that would eventually support enormous biodiversity. But the nutrient pulse accompanying forest expansion poisoned oceans for millions of years. This illustrates a fundamental principle. Ecosystems are interconnected, and changes in one domain propagate to others in unpredictable ways. The first forests couldn't have evolved any awareness that their existence would suffocate marine life thousands of miles away. They simply grew, reproduced, and spread across available landscapes. The ocean paid the price. Recovery from the late Devonian extinctions occurred gradually over the early Carboniferous period. Marine diversity slowly rebuilt, but the composition of communities changed fundamentally. The massive reef structures built by stromatoporoids and Devonian corals never returned in the same form. Carboniferous reefs, when they developed, were constructed by different organisms with different ecological requirements. Placoderms, eliminated by the extinction, left ecological vacancies that sharks and bony fish filled. The structure of marine food webs shifted from placoderm-dominated systems to ones more similar to modern oceans, with sharks and teleost fish as primary large predators. The late Devonian also demonstrates that mass extinctions don't require single catastrophic triggers. Unlike the Chicxulub impact or the Siberian Traps eruptions, discrete events that can be pointed to and dated precisely. The late Devonian involved complex interactions between biological evolution, nutrient cycling, ocean chemistry, and climate over millions of years. No single moment defines when the extinction began or ended. Instead, it represents a prolonged interval of instability, where Earth systems struggled to reach new equilibrium states. Species went extinct in waves, each wave removing organisms and restructuring ecosystems in ways that influence subsequent waves. The selectivity of survival. Organisms with low oxygen tolerance thriving while those requiring high oxygen perished, shows how environmental change acts as a filter on evolution. Natural selection doesn't operate in a vacuum, but in specific environmental contexts. When those contexts shift, the traits that confer survival advantage shift as well. Fish species that had evolved efficient respiratory systems for reasons unrelated to anoxia suddenly found those traits life-saving. Bottom-dwelling invertebrates that could burrow deep into sediments to avoid predators found those same burrows provided refuge from oxygen-depleted water. Evolution is opportunistic, repurposing existing traits for new challenges. One of the more sobering lessons from the late Devonian concerns the time required for ecosystems to stabilize after major disruptions. Even after individual extinction pulses, ecosystems didn't return to pre-crisis conditions. Instead, they lurched through a series of states, each somewhat different from the last, never achieving the stability and diversity that characterized Middle Devonian marine communities. This suggests that once critical thresholds are crossed, once reefs are eliminated, once anoxia becomes widespread, once food webs simplify, recovery isn't simply a matter of waiting. The system has been fundamentally altered, and rebuilding complexity requires evolution of new species, establishment of new ecological relationships, and accumulation of changes that occur over geological timescales measured in millions of years. The late Devonian extinctions also highlight the importance of oxygen in marine ecosystems. While we often focus on temperature or pH as critical environmental parameters, dissolved oxygen may be equally or more important for marine animal survival. Oxygen requirements constrain where species can live, how large they can grow, and how active they can be. When oxygen concentrations drop below critical thresholds, biology simply ceases. No amount of evolutionary adaptation can overcome the basic biochemical requirement for oxygen in cellular respiration for aerobic organisms. Understanding ancient anoxic events helps scientists predict how modern ocean deoxygenation, driven by warming waters that hold less dissolved oxygen and by nutrient pollution from agriculture, might affect marine biodiversity in coming decades and centuries. Between 720 and 635 million years ago, Earth transformed into something almost unrecognizable, a frozen sphere gleaming white against the blackness of space. Ice sheets advanced from the poles toward the equator, covering continents and spreading across tropical oceans until glaciers reached latitudes where the sun shines directly overhead. Geological evidence suggests that during at least 2 prolonged episodes, ice extended to within 5 to 10 degrees of the equator, and possibly all the way to it, encasing the planet in a frozen shell, potentially a mile thick in places. Average global temperatures may have plummeted to 58 degrees Celsius, cold enough that even equatorial oceans froze over. This wasn't a typical ice age like the one that ended 12,000 years ago, where ice sheets covered northern continents but left tropical regions warm. This was planetary refrigeration so extreme that scientists call it Snowball Earth. Life survived, somehow, but it came perilously close to complete annihilation. When the ice finally melted, the world that emerged was fundamentally different, setting the stage for the explosive diversification of complex animal life that would follow. The concept of Snowball Earth initially seemed too extreme to be credible. When geologist Brian Harland first proposed in the 1960s that glacial deposits found in tropical latitudes indicated near total glaciation, most scientists dismissed the idea as impossible. How could Earth freeze completely without killing all life and remaining frozen permanently? Ice reflects roughly 90% of incoming sunlight. A frozen planet would trap itself in perpetual winter. The hypothesis languished until the 1990s, when geologist Paul Hoffman and colleagues presented compelling evidence from Namibia that glacial deposits there, dated to approximately 635 million years ago, occurred at or near the equator, based on paleomagnetic reconstructions of ancient continental positions. Additionally, these glacial rocks were directly overlain by carbonate rocks, limestones that typically form in warm, shallow seas. The abrupt transition from glacial to tropical conditions suggested rapid, extreme climate swings. The evidence for Snowball Earth comes from multiple geological observations that together paint a consistent picture. Tillites, sedimentary rocks composed of unsorted glacial debris ranging from clay to boulders, occur in formations dated to the Cryogenian period, spanning 720 to 635 million years ago, on every continent. Crucially, paleomagnetic data indicate these rocks formed at low latitudes near the equator. Earth's magnetic field leaves a signature in iron-bearing minerals as rocks form, recording the latitude at which they originated. When geologists measure this paleomagnetic signature in cryogenian glacial deposits from Namibia, Australia, and North America, the results consistently indicate tropical or subtropical positions. Glaciers at the equator require global temperatures far below freezing. Additional evidence comes from dropstones, isolated boulders embedded in fine-grained marine sediments. These form when icebergs carry rocks from land and drop them into the ocean as the ice melts. During Snowball Earth episodes, dropstones occur even in rocks formed in equatorial regions, indicating that icebergs floated in tropical seas. Chemical sediments called cap carbonates, layers of limestone and dolostone up to several hundred feet thick, sit directly atop glacial deposits worldwide. These carbonates have unusual chemical signatures, including extremely negative carbon isotope ratios and distinctive textures, suggesting they precipitated rapidly from seawater, supersaturated with dissolved carbonate minerals, conditions expected when a frozen planet suddenly thaws. 2 major Snowball Earth episodes have been identified. The earlier Sturtian glaciation lasted from approximately 717 to 660 million years ago, an almost incomprehensible 57 million years of ice. The later Minoan glaciation occurred from about 650 to 635 million years ago, lasting perhaps 15 million years. Some evidence suggests a third, earlier glaciation called the Chicxulub around 740 million years ago, though its global extent and severity remain debated. Between the Sturtian and Minoan events, climate appears to have warmed significantly, only to plunge back into deep freeze. This pattern of repeated glaciation suggests that Earth's climate system was highly unstable during the Cryogenian, oscillating between frozen and thawed states. What triggered such extreme glaciation? The most widely accepted hypothesis involves a combination of factors, including continental configuration, volcanic weathering, and runaway feedback loops. During the Cryogenian, most continents were positioned in tropical latitudes, an unusual configuration that enhanced weathering rates. Chemical weathering of rocks, particularly silicate minerals, consumes atmospheric carbon dioxide. Rain combines with CO2 to form carbonic acid, which reacts with minerals in rocks, ultimately locking carbon in carbonate minerals that wash into oceans and settle as seafloor sediments. This weathering acts as a planetary thermostat, removing greenhouse gas and cooling climate. Around 750 to 700 million years ago, the breakup of an earlier supercontinent called Rodinia may have positioned multiple continental fragments in tropical regions, where warm temperatures and abundant rainfall maximized weathering rates. Additionally, volcanic eruptions that occurred during the rifting process created fresh basaltic rocks, particularly susceptible to chemical weathering. As weathering intensified, atmospheric CO2 concentrations dropped. Once they fell below a critical threshold, estimates suggest around 200 parts per million or less, ice sheets began forming at high latitudes. This initiated positive feedback loops that drove runaway glaciation. Ice reflects sunlight far more effectively than dark ocean water or vegetation-covered land. As ice sheets expanded, Earth's albedo, the fraction of incoming sunlight reflected back to space, increased dramatically. More reflection meant less absorbed heat, causing further cooling, allowing ice to expand further. This ice albedo feedback is self-reinforcing. Computer climate models simulating conditions with reduced CO2 and expanding ice sheets show that once ice reaches approximately 30 degrees latitude, the feedback accelerates uncontrollably, driving ice to the equator within perhaps 1,000 years, geologically instantaneous. A frozen ocean creates catastrophic consequences for life. Photosynthesis requires sunlight, and ice a mile thick would block nearly all light from reaching the ocean beneath. Marine algae and cyanobacteria that form the base of oceanic food chains would have died en masse. Without photosynthesis producing oxygen, atmospheric oxygen concentrations would have dropped as respiration and chemical reactions consumed it without replenishment. Some researchers estimate that oxygen levels may have fallen to a small fraction of pre-glaciation concentrations, creating anoxic or near-anoxic conditions in many environments. Yet life survived. The question is how. One possibility involves thin spots or cracks in the ice near the equator, where intense tropical sunlight might have kept ice thinner or created seasonal melt zones. Even a few meters of ice over equatorial oceans would allow some light penetration, potentially supporting minimal photosynthesis. Another survival strategy involves hydrothermal vents, underwater hot springs on the seafloor where volcanic activity releases heat and chemicals. These oases of warmth in a frozen ocean could have sustained microbial communities independent of sunlight. Modern hydrothermal vent ecosystems support bacteria that derive energy from chemical reactions rather than photosynthesis, and similar communities might have persisted through snowball episodes. Evidence that life survived comes from molecular clock studies, analyses of genetic differences among modern organisms to estimate when their lineages diverged. These studies indicate that major groups of algae, including red and green algae, existed before and after the Cryogenian glaciations, suggesting they survived through the freeze. Fossilized remains of photosynthetic organisms have been found in rocks immediately following snowball episodes. indicating that these lineages didn't go extinct, but rather persisted through the glaciation and rebounded afterward. Escape from the frozen state required breaking the ice albedo feedback, and the mechanism involves volcanic outgassing. Even with the surface frozen, Earth's interior remained hot, and volcanic eruptions continued, particularly at mid-ocean ridges and subduction zones. Volcanoes release carbon dioxide continuously. Under normal conditions, weathering removes CO2 at roughly the rate volcanism adds it, maintaining equilibrium. But when the planet freezes, weathering essentially stops. Ice-covered continents don't weather, and chemical reactions slow dramatically at low temperatures. Volcanoes kept erupting, adding CO2 to the atmosphere with nothing removing it. Over millions of years, carbon dioxide accumulated to extraordinary concentrations. Climate models suggest that escape from Snowball Earth required atmospheric CO2 to reach levels 350 to 700 times higher than pre-industrial concentrations, perhaps 100,000 to 200,000 parts per million. At such extreme levels, greenhouse warming finally overcame the cooling effect of ice reflection. The ice began melting, starting at the equator where sunlight was strongest. Once melting began, feedback loops again took over, but now in reverse. Darker ocean water absorbed more heat than white ice, accelerating melting. As more ocean surface was exposed, more heat was absorbed, driving further melting. Deglaciation may have occurred within just a few thousand years, catastrophically, rapid compared to the millions of years required for the ice to accumulate. The transition from frozen to thawed created extreme conditions. With CO2 levels hundreds of times higher than normal and ice albedo feedback no longer cooling the planet, temperatures soared. Global average temperatures might have exceeded 122 degrees Fahrenheit during the immediate post-glacial greenhouse. The intense heat drove an extraordinary hydrological cycle with massive rainfall that accelerated weathering of rocks exposed by retreating ice. This explains the cap carbonates found atop glacial deposits worldwide. The combination of high CO2, warm temperatures, and intense weathering released enormous quantities of calcium and carbonate ions into the ocean, where they precipitated as thick limestone layers. The chemical signatures preserved in cap carbonates provide additional clues about post-glacial conditions. Carbon isotope ratios in these rocks show extreme negative values, indicating that the carbon came from sources depleted in carbon-13, either from organic matter that had been locked away during the glaciation or from volcanic CO2 that accumulated over millions of years. The rapid precipitation of such thick carbonate layers required supersaturated ocean conditions that could only develop during the extraordinary transition from frozen to greenhouse states. Some cap carbonates contain structures called tubestone textures, elongated crystal fans that suggest rapid precipitation in warm, CO2-rich waters. The biological consequences of Snowball Earth episodes remain debated but appear profound. While life survived, the extreme environmental stress likely acted as an evolutionary filter, eliminating less adaptable lineages and favoring organisms capable of surviving in refugia or entering dormant states. Some researchers propose that the stress of snowball conditions drove evolutionary innovations in cellular complexity and metabolic flexibility. Eukaryotic cells, complex cells with nuclei and internal structures, had existed for hundreds of millions of years before the Cryogenian, but multicellular organisms remained relatively simple. The snowball episodes may have created selective pressure favoring organisms that could form cooperative multicellular structures, share resources, and survive harsh conditions through collective strategies rather than individual endurance. The timing is suggestive. The final Snowball Earth episode ended around 635 million years ago. Within 50 million years, a geological eye blink, the Ediacaran fauna appeared, Earth's first large, complex multicellular organisms. By 541 million years ago, the Cambrian explosion had begun, diversifying animal body plans and creating most major animal groups we recognize today. While correlation doesn't prove causation, many scientists propose that Snowball Earth acted as a trigger or catalyst for this evolutionary radiation. The extreme environmental challenge may have cleared ecological space of incumbent organisms and favored new, more complex forms. Additionally, the post-glacial ocean, chemistry, enriched with nutrients from intense weathering, may have provided abundant resources supporting rapid diversification. Snowball Earth also illustrates the profound instability possible in Earth's climate system. The planet can exist in multiple stable states: temperate climates like those of most of Earth's history, or frozen states like the cryogenian glaciations. Transitions between these states occur when critical thresholds are crossed, triggering positive feedbacks that drive the system rapidly toward a new equilibrium. This bistability means that relatively modest changes in factors like atmospheric CO2 or continental configuration can have wildly disproportionate effects if they push the system past a tipping point. The question of whether Snowball Earth could happen again depends on continental configuration and atmospheric composition. With continents currently distributed across various latitudes rather than clustered in the tropics, weathering rates are lower and less susceptible to runaway CO2 drawdown. Additionally, the Sun has brightened by about 6% since the cryogenian due to gradual changes in stellar evolution. A dimmer Sun during the Precambrian made Earth more susceptible to freezing. Modern atmospheric CO2 concentrations, elevated by human activities, also make near-term global glaciation virtually impossible. However, on timescales of hundreds of millions of years, if continents again cluster in tropical latitudes and CO2 levels drop through weathering or other processes, another snowball episode could theoretically occur. The cap carbonates that mark the end of snowball episodes represent some of the most rapid sediment accumulation rates known in the geological record. In some locations, hundreds of feet of carbonate rock accumulated in perhaps 10,000 to 100,000 years, rates thousands of times faster than typical marine carbonate deposition. This extraordinary precipitation required ocean chemistry far from equilibrium, supersaturated with dissolved minerals and undergoing massive chemical adjustments as the climate system restabilized. The ocean had essentially been locked in a freezer for millions of years, accumulating volcanic CO2 that dissolved into what liquid water existed. When the ice melted and temperatures soared, this stored CO2 drove intense weathering and carbonate precipitation, literally raining limestone from supersaturated seas. Snowball Earth demonstrates that Earth's habitability isn't guaranteed or permanent. For tens of millions of years, the planet existed in a state hostile to most complex life, with frozen oceans, minimal photosynthesis, and atmospheric oxygen levels potentially too low to support animal respiration. Only the fortunate combination of continued volcanic outgassing and the eventual buildup of sufficient greenhouse gases to break the freeze allowed the planet to return to habitable conditions. Had volcanic activity been lower, or had some other factor prevented CO2 accumulation, Earth might have remained frozen indefinitely, and complex life as we know it might never have evolved. The cryogenian glaciations also highlight the interconnectedness of Earth's systems over geological time. Continental drift driven by plate tectonics influenced weathering rates and atmospheric composition. Atmospheric composition controlled climate and ice extent. Ice extent affected ocean chemistry and biology. Biology influenced atmospheric oxygen levels and carbon cycling. These systems don't operate independently, but form a complex web of feedbacks and interactions. Understanding Snowball Earth requires grasping how changes in one domain propagate through others, creating cascades that can drive the entire planet into radically different states. 74,000 years ago, the island of Sumatra in present-day Indonesia tore itself apart in one of the most powerful volcanic eruptions Earth has witnessed in the past 2 million years. The Toba supervolcano ejected approximately 670 cubic miles of rock, ash, and volcanic material into the atmosphere, roughly 5,000 times more than Mount St. Helens released in 1980, and 100 times more than the 1815 eruption of Mount Tambora that caused the year without a summer. The explosion excavated a caldera, a massive volcanic crater, measuring 62 miles long and 19 miles wide, which subsequently filled with water to become Lake Toba, the largest volcanic lake on Earth. But the true devastation wasn't measured in cubic miles of ejected rock or the size of the crater left behind. It was measured in the atmospheric effects that followed. Sulfur dioxide and ash particles injected into the stratosphere blocked sunlight for years, dropping global temperatures by an estimated 7 to 9 degrees Fahrenheit, and triggering a volcanic winter that may have lasted a decade or more. Some researchers propose that this eruption pushed humanity to the brink of extinction, reducing global human populations to fewer than 10,000 individuals, a genetic bottleneck that left its signature in the DNA of every person alive. Today, the Toba volcano sits along the Sunda Arc, a chain of volcanic islands formed where the Indo-Australian tectonic plate subducts beneath the Eurasian plate. As oceanic crust descends into the mantle, it releases water and other volatiles that lower the melting point of the overlying mantle rock, generating magma that rises toward the surface. Most subduction zone volcanoes produce relatively modest eruptions every few decades or centuries. But occasionally, magma accumulates in massive chambers beneath the surface, building pressure over hundreds of thousands of years. When these supervolcanic systems finally erupt, they release volumes of material thousands of times greater than typical volcanic eruptions. Toba's 74,000 year ago eruption, the most recent of at least 3 major eruptions, from this volcanic system over the past million years, represents one of the largest volcanic events of the Quaternary period. Evidence of the eruption's magnitude comes from ash, deposits found across an enormous geographic area. The youngest Toba tuff, as geologists call this distinctive ash layer, has been identified in sediment cores from the Indian Ocean, the South China Sea, and the Arabian Sea. On land, ash deposits up to 15 feet thick occur in central India, over 1,800 miles from the eruption source. In Malaysia, just a few hundred miles from Toba, ash layers exceed 30 feet in depth. The ash consists of distinctive glass shards and mineral crystals that allow geologists to trace it back to its source through chemical fingerprinting. Finding this ash layer in such distant locations indicates that volcanic material circled the globe, entering the stratosphere where high-altitude winds distributed it across vast distances. The eruption column likely reached heights exceeding 50 miles, well into the stratosphere and potentially touching the mesosphere. Material injected this high remains suspended for years, slowly settling back to Earth's surface while blocking and scattering incoming sunlight. Climate models simulating a Toba-scale eruption suggest that sulfur aerosols in the stratosphere could have reduced sunlight reaching Earth's surface by 25% to 90%, depending on latitude and season, with the most severe reductions occurring in the tropics near the eruption site. Surface temperatures in Southeast Asia may have dropped by 27 degrees or more during the first few years after the eruption. Even regions far from Toba experienced cooling of 7 to 11 degrees based on climate simulations. The impact on vegetation would have been catastrophic. Reduced sunlight limits photosynthesis, and combined with sharply cooler temperatures, growing seasons would have shortened dramatically or ceased entirely in many regions. Pollen analysis from lake sediments in India shows a shift in vegetation composition at the level of the Toba ash layer, with tropical forest species declining and being replaced by grasslands and cold-adapted plants. This vegetation collapse would have cascading effects through food chains, eliminating herbivores' food sources and subsequently affecting predators including early human populations. Archaeological evidence from sites in India provides direct glimpses of how human populations were affected. Stone tool assemblages found below the Toba ash layer differ from those found above it, suggesting cultural disruption or population replacement. Some archaeological sites show evidence of continuous human occupation through the ash layer, indicating that at least some groups survived locally, though possibly in reduced numbers. The debate centers on how severe and widespread the population crash was. Did Toba reduce humanity to a few thousand individuals clinging to survival in isolated refugia? Or did populations decline significantly but not catastrophically? Genetic evidence adds a crucial dimension to this question. Studies of human mitochondrial DNA and Y chromosome variation show that all modern humans descend from populations that went through a severe bottleneck, a period when population sizes crashed to very low levels, sometime between 50,000 and 100,000 years ago. The timing overlaps intriguingly with the Toba eruption at 74,000 years ago. Population geneticists analyzing the diversity of modern human DNA calculate that effective population sizes may have dropped to between 3,000 and 10,000 breeding individuals during this bottleneck. For comparison, there are currently more than 100,000 orangutans in the wild. If the genetic bottleneck hypothesis is correct, humanity was more endangered 74,000 years ago than orangutans are today. However, the connection between Toba and the genetic bottleneck remains contentious. Some researchers argue that the timing is too uncertain. Genetic dating methods have large error margins, and the bottleneck could have occurred before or after Toba. Others point out that human populations in Africa, far from the eruption, should have been less affected than Asian populations. Yet the genetic bottleneck appears global. Alternative explanations for the bottleneck include climate changes associated with the transition into the last glacial period, or simply the normal population dynamics of a species expanding out of Africa, with small founding populations colonizing new regions. Recent archaeological discoveries complicate the picture further. Sites in South Africa show continuous occupation and technological innovation through the period of the Toba eruption, suggesting that populations there remained stable and creative despite any global climate effects. Stone tool technology actually advanced during this period in some African sites, with the development of more sophisticated hafting techniques and composite tools. This doesn't necessarily contradict a bottleneck. Refugia in favorable locations could have maintained viable populations, but it suggests the impact wasn't uniformly catastrophic. The volcanic winter following Toba would have created a world of hardship for early humans. Hunter-gatherer populations require extensive territories to sustain themselves, and the collapse of plant productivity would have forced competition for dwindling resources. Groups might have been pushed into coastal areas where marine resources provided more reliable food sources, or into tropical refugia where climate impacts were less severe. The cooling would have been most extreme in mid-latitudes and continental interiors, while tropical coasts and certain valley systems might have maintained more moderate conditions. Animal populations suffered as well. Paleontological evidence from India and Southeast Asia shows changes in mammal communities around the time of Toba, though disentangling volcanic effects from broader climate trends of the period proves difficult. The eruption occurred during a time of general climate cooling, as Earth moved deeper into the last glacial period, and separating volcanic impacts from these longer-term trends remains challenging. Some researchers propose that Toba accelerated ongoing population declines rather than causing entirely new extinctions. The Toba caldera itself filled with water over subsequent millennia, creating Lake Toba, which remains today as a spectacular reminder of the eruption's power. The lake reaches depths exceeding 1,600 feet and contains an island, Samosia Island, that formed from resurgent magma pushing up the caldera floor after the eruption. Geophysical surveys of the caldera structure reveal that magma chambers beneath Toba continue to exist, and the volcano remains potentially active. Small eruptions have occurred in the past few thousand years, and monitoring systems track seismic activity and ground deformation that might signal future magmatic activity, while another super-eruption appears unlikely in the near future. Such events require hundreds of thousands of years to accumulate sufficient magma. The possibility reminds us that supervolcanoes remain one of the few natural phenomena capable of causing global catastrophe. Toba demonstrates that volcanic eruptions, even without direct impact on most of the planet, can create worldwide environmental crises through atmospheric effects. The immediate blast zone covered only a few hundred miles, but sulfur aerosols circled the globe for years. This illustrates the interconnectedness of Earth's systems. An event on a single Indonesian island affected temperatures, vegetation, and potentially human evolution on every continent. Understanding Toba helps scientists model potential impacts of future supervolcanic eruptions and provides context for assessing other volcanic hazards. While super-eruptions occur only every 50,000 to 100,000 years on average, their capacity to disrupt global climate and civilization makes them worthy of continued study and monitoring. 12,800 years ago, Earth was warming. The last great ice age was releasing its grip on the northern hemisphere. Massive ice sheets that had covered Canada and Scandinavia were melting, retreating northward as temperatures climbed. Sea levels rose by hundreds of feet as glacial meltwater flooded back into the oceans. Forests advanced across landscapes that had been tundra for millennia. Human populations expanded into newly habitable territories, developing increasingly sophisticated tool technologies and social structures. Then suddenly and without warning, the warming stopped. Temperatures plummeted back toward near-glacial conditions within perhaps a few decades, possibly even faster. The Younger Dryas stadial, as paleoclimatologists call this climate reversal, lasted approximately 1,300 years, from 12,800 to 11,500 years ago. During this interval, temperatures in the northern hemisphere dropped by 9 to 18 degrees. Glaciers advanced, and ecosystems that had begun adapting to warming were thrown back into cold-adapted states. Then, just as abruptly as it began, the Younger Dryas ended, and warming resumed even more rapidly than it had been interrupted. What caused this extraordinary climate whiplash remains debated, but the consequences transformed both natural ecosystems and early human societies in ways that may have influenced the development of agriculture and civilization. The evidence for the Younger Dryas comes from multiple sources that together reveal its global reach and severity. Ice cores drilled from the Greenland ice sheet contain annual layers of accumulated snow that preserve a record of past climate extending back more than 100,000 years. Oxygen isotope ratios in the ice reflect the temperature at which snow formed. Colder temperatures produce ice enriched in lighter oxygen 16, while warmer temperatures favor heavier oxygen 18. When scientists analyze Greenland ice cores, they find a dramatic shift in isotope ratios at precisely 12,800 years ago, indicating an abrupt temperature drop. The transition occurs over just a few decades in the ice core record, suggesting the climate shift happened with stunning rapidity. Lake sediment cores provide complementary evidence. Pollen grains preserved in lake muds record the vegetation surrounding the lake when each layer was deposited. In lakes across Europe and North America, pollen assemblages show a clear pattern. Tree pollen declines sharply at the start of the Younger Dryas, replaced by pollen from tundra plants like grasses. Sedges and dwarf shrubs adapted to cold conditions. Forests retreated southward or to lower elevations, replaced by the treeless landscapes characteristic of periglacial environments. When the Younger Dryas ended 11,500 years ago, tree pollen rapidly increased again as forests recolonized. The name Younger Dryas comes from Dryas octopetala, a cold-adapted flowering plant whose pollen became abundant in European lake sediments during this interval. The Younger distinguishes it from two earlier cold periods, the Oldest Dryas and Older Dryas, that occurred during the overall deglaciation sequence. The Younger Dryas was the last and most severe of these cold reversals, and the only one with clear global impacts. What triggered such a rapid climate reversal? The leading hypothesis involves disruption of Atlantic Ocean circulation. The Atlantic Meridional Overturning Circulation, AMOC, acts as a massive conveyor belt transporting warm surface water from the tropics northward toward the Arctic, where it releases heat, cools, becomes denser, and sinks to flow southward at depth. This circulation delivers enormous quantities of heat to northern Europe and the North Atlantic region, moderating climate. Climate models show that if this circulation weakens or shuts down, temperatures in the North Atlantic and surrounding continents can drop dramatically within years to decades. The mechanism for shutting down the AMOC involves fresh water. The sinking of cold, dense water in the North Atlantic drives the entire circulation system, and this sinking depends on water being sufficiently salty and dense. Fresh water is less dense than salt water and doesn't sink as readily. During deglaciation, enormous volumes of fresh water from melting ice sheets poured into the North Atlantic. Most of this meltwater likely flowed through the Mississippi River system into the Gulf of Mexico, or through the St. Lawrence River into the North Atlantic. But geological evidence suggests that approximately 12,900 years ago, drainage patterns changed catastrophically. A massive glacial lake called Lake Agassiz had formed along the southern margin of the retreating North American ice sheet, covering areas of modern Manitoba, Saskatchewan, North Dakota, and Minnesota. This lake contained more water than all current Great Lakes combined. Geological evidence indicates that around the onset of the Younger Dryas, Lake Agassiz suddenly drained, releasing thousands of cubic miles of fresh water into the North Atlantic. The influx of this fresh water would have reduced surface water density, preventing sinking and shutting down, or severely weakening the AMOC. Without heat transport from the south, temperatures around the North Atlantic plummeted. However, an alternative and more controversial hypothesis proposes an extraterrestrial trigger. In 2007, researchers proposed that an airburst, or impact from a disintegrating comet, occurred over North America approximately 12,900 years ago precisely, coinciding with the onset of the Younger Dryas. They pointed to a layer enriched in microscopic diamonds, magnetic spherules, carbon spherules, and other materials they interpreted as impact markers, found at numerous sites across North America at the Younger Dryas boundary. They also noted the apparent extinction or severe decline of North American megafauna. Mammoths, mastodons, ground sloths, saber-toothed cats, and the disappearance of the Clovis culture, a distinctive archaeological tradition, around this same time. The impact hypothesis suggests that the comet airburst or multiple impacts triggered massive wildfires across North America, destabilized the ice sheet causing rapid meltwater release, and directly caused the megafaunal extinctions and human cultural disruptions. Critics have challenged nearly every aspect of this hypothesis. Subsequent studies have questioned whether the proposed impact markers are actually diagnostic of impacts or could form through other processes. The timing of megafaunal extinctions appears more gradual than a single catastrophic event would produce, and the Lake Agassiz drainage provides a sufficient explanation for AMOC shutdown without requiring an impact. The debate continues, with proponents of the impact hypothesis presenting additional evidence and critics countering with alternative explanations. What remains clear is that something dramatic happened 12,800 years ago, and the consequences reshaped both natural and human worlds. The Younger Dryas cooling hit North America and Europe hardest, but evidence from tropical regions, the southern hemisphere, and even Antarctica shows climate shifts during this interval, suggesting global atmospheric and oceanic circulation changes rather than purely regional effects. North American megafauna extinctions cluster around the Pleistocene-Holocene transition, though dating uncertainties make it difficult to determine whether extinctions occurred rapidly at the Younger Dryas onset or more gradually over several thousand years. Mammoths and mastodons disappeared from most of their range, surviving only in isolated pockets. Giant ground sloths, horses, camels, dire wolves, and short-faced bears vanished from the continent. Whether climate change, human hunting, disease, or a combination drove these extinctions remains debated, but the Younger Dryas certainly added environmental stress during a period when these species were already declining. Human populations faced significant challenges. The Clovis culture, characterized by distinctive fluted projectile points found across North America, appears to decline or transform around the onset of the Younger Dryas. Archaeological sites show changes in tool technologies, subsistence strategies, and possibly population distributions. Some researchers propose that the disappearance of megafauna forced human populations to shift towards smaller game, plant foods, and more diverse subsistence strategies. In the Near East, hunter-gatherer populations that had begun experimenting with cultivation of wild cereals during the warm period before the Younger Dryas may have intensified these efforts during the cold reversal, setting in motion processes that would lead to full-scale agriculture after the climate warmed again. The Younger Dryas demonstrates how rapidly Earth's climate can shift when critical thresholds are crossed. The transition into the cold interval occurred over decades. The transition out appears even more abrupt. Ice core records suggest Greenland temperatures rose by 18 degrees Celsius in less than a decade when the Younger Dryas ended. Such rapid shifts challenge our assumptions about climate stability and reveal the potential for dramatic changes occurring within human lifetimes, rather than over centuries or millennia. Ocean circulation changes, triggered by freshwater inputs, provide a plausible mechanism for sudden climate shifts without requiring asteroid impacts. The AMOC system has shifted between strong and weak states multiple times during the glacial-interglacial cycles of the past million years, and each shift corresponded to rapid climate changes. The Younger Dryas may represent the most recent major example of this phenomenon. Current concerns about Greenland ice sheet melting potentially weakening the AMOC draw direct parallels to the Younger Dryas event, suggesting that modern climate systems retain the capacity for rapid, threshold-driven transitions. The end of the Younger Dryas around 11 to 500 years ago marks the beginning of the Holocene epoch, the current interglacial period in which human civilization developed. The rapid warming that followed the cold interval created conditions favorable for agriculture in multiple regions worldwide. In the Fertile Crescent of the Near East, populations that had experimented with plant cultivation during and after the Younger Dryas transitioned to full agricultural economies within the next few thousand years. Similar transitions occurred independently in China, Mesoamerica, and other regions. Whether the climate stress of the Younger Dryas directly prompted agricultural development remains debated, but the timing suggests connections between environmental challenges and human innovation. The Younger Dryas also affected ecosystems in ways that persisted long after the cold interval ended. Species that had begun migrating northward during the initial deglaciation were forced to retreat southward again during the Younger Dryas, then recolonized northern areas when warming resumed. These repeated range shifts created genetic bottlenecks in some populations and mixing of previously isolated populations in others, leaving signatures visible in modern genetic diversity patterns of many plant and animal species. Geological records show that the abrupt warming ending, the Younger Dryas, triggered rapid glacier retreat and accelerated sea level rise. Coastal areas flooded as glacial ice melted, forcing human populations to adapt to changing shorelines. Underwater archaeological sites now submerged off modern coastlines may contain evidence of human settlements established during the Younger Dryas when sea levels were lower. The famous Black Sea flood hypothesis proposes that rising Mediterranean waters catastrophically breached the Bosporus around 7,500 years ago, flooding a freshwater lake and creating the modern Black Sea. Though this occurred several thousand years after the Younger Dryas, it resulted from the same ongoing deglaciation and sea level rise processes. The Younger Dryas stands as a powerful reminder that Earth's climate is not gradually predictable but capable of abrupt shifts when systems cross critical thresholds. The event demonstrates that warming trends can reverse dramatically, that ocean circulation plays crucial roles in regional climate, and that environmental changes occurring over decades can have consequences lasting millennia. For early human societies, the Younger Dryas represented both challenge and opportunity, forcing adaptation but potentially catalyzing innovations that would fundamentally reshape human existence. Understanding the Younger Dryas helps scientists assess risks of future abrupt climate changes, while the specific conditions that triggered this event, massive glacial lakes, retreating ice sheets, and fresh water flooding into the North Atlantic, don't exist today. The underlying mechanisms remain relevant. The AMOC continues to transport heat northward, and evidence suggests it has weakened in recent decades. Whether current changes could trigger another abrupt climate shift remains uncertain, but the Younger Dryas proves such shifts are possible and can occur with stunning rapidity. The past doesn't predict the future perfectly, but it reveals what Earth's climate system is capable of when pushed beyond stable states. 56 million years ago, Earth experienced one of the most rapid and extreme warming events in its entire geological history. Within perhaps 20,000 years, a geological eye blink, global temperatures spiked by 9 to 14 degrees, and they remained elevated for approximately 200,000 years before gradually returning to pre-event levels. This episode, called the Paleocene-Eocene Thermal Maximum, or PETM, transformed the planet. The Arctic Ocean warmed to subtropical temperatures, where palm trees and alligator relatives thrived in latitudes now locked in permafrost. Deep ocean temperatures rose from around 50 degrees Celsius to nearly 68 degrees Celsius, eliminating temperature gradients that normally stratify ocean layers. Tropical regions became so hot that they may have approached the upper thermal limits for mammalian life. The warming triggered massive extinctions in deep-sea environments, where an estimated 35% to 50% of benthic foraminiferous species, microscopic organisms living on the seafloor, vanished. On land, mammals underwent dramatic body size reductions and intercontinental migrations as ecosystems restructured. The PETM serves as a natural experiment revealing how Earth's climate responds to massive, rapid carbon injection, making it eerily relevant to modern concerns about anthropogenic climate change. The evidence for the PETM appears in rock formations worldwide as a distinctive, clay-rich layer marking the boundary between the Paleocene and Eocene epochs. Marine sediment cores show that carbonate-rich sediments typical of deep-sea environments abruptly give way to carbonate-poor clays at precisely 56 million years ago. This carbonate dissolution indicates that the ocean became acidic, dissolving calcium carbonate shells and skeletons on the seafloor. The same boundary layer contains a dramatic negative carbon isotope excursion, a sharp drop in the ratio of carbon-13 to carbon-12 that signals massive input of isotopically light carbon into the atmosphere and oceans. The carbon isotope signature provides crucial clues about what caused the warming. Different carbon sources have different isotopic signatures. Volcanic CO2 has moderate carbon-13 values. Organic carbon from plants and plankton is depleted in carbon-13, and methane is extremely depleted. The PETM excursion shows carbon-13 values, indicating that approximately 3,000 to 7,000 gigatons of carbon, possibly more, entered the Earth system rapidly. The isotopic composition suggests this carbon came either from massive methane release or from oxidation of organic carbon, not from volcanism alone. The leading hypothesis involves methane hydrates, ice-like compounds containing methane trapped in molecular cages of frozen water. These hydrates form under high pressure and low temperature conditions, typical of deep ocean sediments and Arctic permafrost. Modern oceans contain enormous quantities of methane hydrates, estimated at several thousand gigatons of carbon. When ocean temperatures rise or pressures decrease, the hydrates destabilize and release methane gas. Methane is a potent greenhouse gas, roughly 25 to 80 times more effective than CO2 at trapping heat over short timescales. Once released, atmospheric methane oxidizes to CO2 within decades, but the greenhouse warming persists for thousands of years. What triggered the initial warming that destabilized methane hydrates? Several factors may have converged. Tectonic activity in the North Atlantic was creating new oceanic crust as Greenland separated from Europe, and volcanic activity associated with this rifting released CO2 into the atmosphere. Additionally, orbital variations may have caused solar heating of high latitudes where methane hydrates were concentrated. The initial warming from volcanic CO2, or orbital forcing, would have heated ocean waters, destabilizing hydrates and releasing methane. This methane caused additional warming, which destabilized more hydrates, creating a runaway feedback loop that drove temperatures upward until the carbon source was exhausted. The environmental consequences transformed Earth's ecosystems. In the oceans, the combination of warming, acidification, and oxygen depletion created hostile conditions for deep-sea life. Benthic foraminifera that had thrived for millions of years disappeared, replaced by opportunistic species tolerant of extreme conditions. Surface-dwelling planktonic organisms experienced disruptions as well, though extinction rates were lower than for seafloor dwellers. Coral reefs suffered, and calcifying organisms generally declined as acidified waters made shell building energetically expensive or impossible. On land, mammals showed striking responses to the warming. Fossil evidence from Wyoming's Bighorn Basin, one of the most completely studied records of the PETM, reveals that many mammal species underwent rapid body size reductions. The earliest horses, small dog-sized animals called Siphohippus, decreased from roughly 12 pounds to about 8.5 pounds over the first 130,000 years of the PETM, a 30% size reduction. Other mammal groups showed similar dwarfing patterns. This body size reduction likely represents an evolutionary response to heat stress and nutritional changes, as smaller animals have higher surface area to volume ratios that facilitate heat dissipation, and smaller body sizes reduce overall food requirements in environments where productivity was stressed. Vegetation underwent dramatic shifts. Fossil leaf assemblages from the Bighorn Basin show that diverse temperate forests were rapidly replaced by plant communities dominated by members of the legume family, which can fix atmospheric nitrogen through symbiotic bacteria in their root nodules. This shift suggests that weathering rates had accelerated dramatically. The intense rainfall characteristic of greenhouse climates accelerates rock weathering, which removes nutrients like phosphorus and calcium from soils. Nitrogen-fixing plants would have had competitive advantages in these nutrient-depleted soils. The dominance of legumes persisted for thousands of years until weathering delivered fresh nutrients from bedrock and more. Diverse plant communities could re-establish. Evidence from high-latitude regions shows that tropical and subtropical ecosystems extended far beyond their modern ranges. Fossil pollen from sediment cores in the Arctic Ocean indicates that during the PETM, this region supported forests including palms, cycads, and other warmth-loving plants. Crocodilian fossils occur in formations from Wyoming and Canada that represent latitudes of 50–60 degrees, far north of crocodilians' modern cold tolerance limits. These findings indicate that winter temperatures, even at high latitudes, remained above freezing throughout the PETM, eliminating the polar ice that existed before and after the event. The tropical regions present a more puzzling picture. Computer climate models simulating PETM conditions struggle to reproduce the extreme warmth inferred from high-latitude fossil and geochemical evidence without making tropical regions lethally hot, exceeding 122 degrees or more. Yet tropical forests appear to have persisted, suggesting either that models overestimate tropical warming or that organisms possessed greater heat tolerance than modern species. Some researchers propose that increased cloud cover or changes in atmospheric circulation patterns could have moderated tropical temperatures while still allowing extreme polar warming, but this remains an active area of research. Ocean circulation patterns underwent fundamental reorganization. The thermohaline circulation that today delivers heat poleward depends on temperature and salinity gradients between equatorial and polar waters. During the PETM, with minimal temperature difference between tropics and poles, this circulation likely weakened dramatically or reconfigured into entirely different patterns. Evidence from marine sediments suggests that deep ocean circulation slowed, potentially leading to oxygen depletion in deeper waters. Some sediment cores show laminated layers lacking bioturbation, the mixing caused by burrowing organisms, suggesting that seafloor environments became anoxic and uninhabitable. The recovery from the PETM occurred gradually over approximately 200,000 years as excess carbon was removed from the atmosphere through weathering and burial in sediments. Accelerated weathering rates during the hot, wet climate drew down CO2, while the ocean absorbed carbon and deposited it in carbonate and organic-rich sediments. Marine ecosystems slowly rebuilt, though the communities that emerged differed from those that had existed before. Mammalian body sizes gradually increased again, though not all lineages returned to pre-PETM sizes. Vegetation patterns shifted as climate cooled and nutrient availability changed. The PTM provides crucial insights into how Earth's climate system responds to rapid carbon release. The warming magnitude, the carbon isotope excursion, the ocean acidification, and the recovery timescales all offer natural experiments that scientists use to test climate models and understand feedback mechanisms. One sobering finding: the recovery took 200,000 years, even though the initial warming occurred in perhaps 20,000 years or less. This asymmetry, rapid onset, slow recovery, appears characteristic of carbon-driven warming events. Once excess CO2 enters the atmosphere, natural processes remove it slowly through weathering and sedimentation operating over hundreds of thousands of years. Comparing the PETM to modern climate, change reveals both similarities and critical differences. The total amount of carbon released during the PETM, 3,000 to 7,000 gigatons, is comparable to estimates of economically recoverable fossil fuel reserves. However, the PETM carbon release occurred over at least 20,000 years, while humans are releasing comparable amounts in just a few centuries, a rate roughly 100 times faster. This means modern climate is being forced at rates exceeding even the extreme conditions of the PETM, potentially limiting the ability of ecosystems and evolution to keep pace with changing conditions. The PETM also demonstrates that Earth's climate has tipping points where feedbacks can cause runaway warming. The methane hydrate feedback, where warming releases methane, which causes more warming, which releases more methane, represents exactly the kind of positive feedback that climate scientists warn about in modern contexts. While methane hydrate destabilization doesn't appear imminent in current climate projections, the pattern proves such mechanisms exist and can dramatically amplify warming beyond what initial forcings alone would produce extinction. Patterns during the PTM reveal the importance of extinction location and ecosystem type. Deep-sea environments, isolated and stable for millions of years, suffered severe extinctions when conditions changed rapidly. Organisms living in variable environments like coastal zones or terrestrial settings showed lower extinction rates, presumably because they already possessed adaptations to environmental variability. This suggests that stable environments produce specialists that are vulnerable to rapid change, while variable environments select for generalists with broader tolerances. The PETM influenced the subsequent evolution of mammals in ways that persist today. Many modern mammal orders first appeared or diversified during and immediately after the PETM, including primates, the lineage leading to humans. The environmental disruptions may have created ecological opportunities by eliminating incumbent species and restructuring ecosystems in ways that favored certain lineages. The appearance of primates in North America, Europe, and Asia during the PETM suggests that warm, forested conditions extending to high latitudes allowed tropical adapted groups to expand their ranges across continents that are now separated by climatic barriers. Understanding the PETM helps scientists predict consequences of ongoing anthropogenic climate change. While no historical analogy is perfect, continental positions, solar output, and biological communities differ between 56 million years ago and today. The PETM demonstrates how Earth's physical and biological systems respond to rapid carbon injection, ocean acidification and extreme warming, the extinctions, ecosystem restructuring, and long recovery times observed during the PETM offer cautionary lessons about the potential consequences of current carbon emissions if they continue unabated. The PETM stands as one of Earth's most dramatic natural experiments in rapid climate change, leaving signatures in rocks worldwide that scientists continue to study for insights into our planet's past and potentially its future. 542 million years ago, Earth's oceans hosted bizarre life forms unlike anything alive today. The Ediacaran period, spanning from 635 to 541 million years ago, saw the first widespread appearance of large, complex, multicellular organisms. These weren't the familiar animals with shells, skeletons, eyes, and mouths that would dominate later oceans. Instead, Ediacaran organisms resembled quilted mattresses, fronds anchored to the seafloor, and strange disc-shaped forms. Some reached lengths exceeding 3 feet, making them the largest organisms Earth had yet produced. They lived in shallow seas worldwide, creating communities that persisted for tens of millions of years. Then, at the end of the Ediacaran, they vanished. Most of these peculiar organisms left no descendants, disappearing from the fossil record just as animals recognizable as arthropods, mollusks, and worms were beginning to diversify in the Cambrian explosion. The end Ediacaran extinction eliminated Earth's first experiment in large multicellular life, clearing the stage for the animal forms that would shape the subsequent 540 million years of evolution. Ediacaran fossils were first recognized in Australia's Ediacaran Hills in 1946, though similar fossils had been found decades earlier in other locations without being understood. These impressions preserved in sandstone showed organisms with radial or bilateral symmetry and complex patterns of segments or branches. Some paleontologists initially interpreted them as early relatives of modern animal groups, jellyfish, sea pens, worms, but closer examination revealed fundamental differences. Many Ediacaran organisms lacked obvious mouths, digestive systems, or locomotive structures. Their body plans didn't fit neatly into any modern animal group. 542 million years ago, Earth's oceans hosted bizarre life forms unlike anything alive today. The Ediacaran period, spanning from 635 to 541 million years ago, saw the first widespread appearance of large, complex, multicellular organisms. These weren't the familiar animals with shells, skeletons, eyes, and mouths that would dominate later oceans. Instead, Ediacaran organisms resembled quilted mattresses, fronds anchored to the seafloor, and strange disc-shaped forms. Some reached lengths exceeding 3 feet, making them the largest organisms Earth had yet produced. They lived in shallow seas worldwide, creating communities that persisted for tens of millions of years. Then, at the end of the Ediacaran, they vanished. Most of these peculiar organisms left no descendants, disappearing from the fossil record just as animals recognizable as arthropods, mollusks, and worms were beginning to diversify in the Cambrian explosion. The end Ediacaran extinction eliminated Earth's first experiment in large multicellular life, clearing the stage for the animal forms that would shape the subsequent 540 million years of evolution. Ediacaran fossils were first recognized in Australia's Ediacaran Hills in 1946, though similar fossils had been found decades earlier in other locations without being understood. These impressions preserved in sandstone showed organisms with radial or bilateral symmetry and complex patterns of segments or branches. Some paleontologists initially interpreted them as early relatives of modern animal groups, jellyfish, sea pens, worms, but closer examination revealed fundamental differences. Many Ediacaran organisms lacked obvious mouths, digestive systems, or locomotive structures. Their body plans didn't fit neatly into any modern animal group. One of the most iconic Ediacaran organisms, Dickinsonia, grew up to 4.5 feet long and consisted of repeated segments arranged in a quilted pattern. It lay flat on the seafloor like a living bath mat. For decades, scientists debated whether Dickinsonia was an animal, a fungus, a lichen, or something entirely different. Recent chemical analysis of organic biomarkers preserved in Dickinsonia fossils revealed cholesterol, a molecule characteristic of animals, finally confirming its animal nature. But it possessed no obvious head, tail, mouth, or anus, raising questions about how it fed and moved. Other Ediacaran forms were equally enigmatic. Charnia resembled modern sea pens, colonial animals related to corals, with a central stalk and repeated branches. Spragina had a crescentic head shield and segmented body suggesting arthropod relationships, yet lacked the jointed appendages characteristic of true arthropods. Tribrachidium bore threefold radial symmetry, a pattern virtually unknown in modern animals, which typically show twofold, fourfold, fivefold, or no symmetry. These organisms represented evolutionary experiments in body construction, solutions to the challenges of multicellular life that differed fundamentally from those that would subsequently prove successful. Ediacaran communities differed ecologically from later marine ecosystems. Most organisms appear to have been sessile, anchored to the seafloor or lying on its surface. Evidence for predation is minimal or absent. No fossils show bite marks, drill holes, or defensive armor. The seafloor was covered by extensive microbial mats, communities of bacteria and algae that provided food and possibly structural support. Many Ediacaran organisms may have fed by absorbing nutrients directly through their body surfaces or through symbiotic relationships with photosynthetic microbes, rather than by actively hunting or grazing. Then, around 550 million years ago, well before the Ediacaran-Cambrian boundary, these communities began declining. Fossil diversity and abundance decreased. By 541 million years ago, at the boundary, the distinctive Ediacaran organisms had essentially disappeared. A few forms may have survived into the earliest Cambrian, but they were rare and soon extinct. In their place, the Cambrian explosion began diversifying animals with mineralized shells, complex eyes, jointed appendages, sophisticated nervous systems, and predatory lifestyles. What caused the end Ediacaran extinction? Unlike many other mass extinctions, no obvious environmental catastrophe marked this boundary. There's no evidence of asteroid impact, massive volcanism, or dramatic climate swings. Instead, the extinction appears biological, driven by competition and predation from newly evolved animals. The appearance of mobile animals with digestive systems and predatory capabilities transformed seafloor ecosystems. Animals that could burrow destroyed the microbial mats that had carpeted Ediacaran seafloors. Without these mats, organisms adapted to living on or within them lost their substrate and food source. Predation itself may have driven extinction. Ediacaran organisms lacked defensive structures, no shells, spines, or toxins. When predatory animals evolved, these soft-bodied, immobile forms became easy prey. The fossil record shows increasing bioturbation, disruption of sediments by burrowing animals, across the Ediacaran-Cambrian boundary, indicating that animal activity was fundamentally restructuring seafloor environments. Organisms adapted to stable, mat-covered substrates couldn't survive in these newly churned, actively mixed sediments. The end Ediacaran extinction demonstrates that biological innovation can drive extinction as effectively as environmental catastrophe. The evolution of complex animals with new feeding strategies, mobility, and ecological engineering capabilities eliminated incumbent organisms not through direct competition alone, but by fundamentally changing the environment. This represents one of the first major examples of ecosystem engineering organisms, modifying their environment in ways that favor themselves but harm others, shaping evolution. The Ediacaran organisms may have represented a dead-end experiment, body plans that worked in the quiet, predator-free oceans of their time, but couldn't survive once more sophisticated animals evolved. Alternatively, some Ediacaran forms may have been early animals whose relationships to modern groups remain obscure due to their unusual preservation and anatomy. The debate continues, but what's clear is that these organisms dominated Earth's oceans for tens of millions of years before being swept away by the Cambrian explosion, their evolutionary experiments abandoned in favor of body plans that would prove more versatile and enduring. Between 50,000 and 10,000 years ago, Earth witnessed the disappearance of giants. Across every continent except Africa and parts of Asia, massive animals that had dominated terrestrial ecosystems for millions of years went extinct within a geological instant. Woolly mammoths that stood 11 feet tall and weighed 6 tons vanished from North America, Europe, and Asia. Giant ground sloths weighing up to 4 tons disappeared from South America. Saber-toothed cats, dire wolves, short-faced bears, giant beavers the size of black bears, and glyptodonts, armored mammals resembling Volkswagen-sized armadillos, all vanished. In Australia, marsupial lions, giant kangaroos standing 10 feet tall, and enormous wombats called diprotodon disappeared. Madagascar lost elephant birds weighing half a ton, and giant lemurs. New Zealand's moas, flightless birds reaching 12 feet tall, went extinct. Approximately 178 species of megafauna, animals weighing more than 100 pounds, disappeared during the late Pleistocene, representing roughly 75% of all large animal species worldwide. Only Africa and Southern Asia retained diverse megafaunal assemblages. The cause of this global catastrophe remains debated, but two suspects dominate: climate change at the end of the last ice age and the expansion of human populations armed with sophisticated hunting technologies. The timing of extinctions varied by continent in ways that provide crucial clues about causation. In Australia, megafaunal extinctions occurred between 50,000 and 40,000 years ago, shortly after humans first arrived on the continent. In North and South America, extinctions clustered between 15,000 and 10,000 years ago, again coinciding with human arrival and population expansion. In Europe and Northern Asia, extinctions occurred more gradually between 40,000 and 10,000 years ago. Only in Africa, where humans had existed for hundreds of thousands of years, did megafauna largely survive. This pattern suggests that human arrival and megafaunal extinction are linked. The overkill hypothesis proposes that human hunting drove extinctions. Large animals produce relatively few offspring and have long generation times, making their populations vulnerable to even modest increases in mortality. Computer models show that if human hunters killed just 1 to 2% more animals per year than populations could replace through reproduction, species would spiral toward extinction within centuries. Large animals are attractive prey. A single mammoth provides thousands of pounds of meat, far more than dozens of rabbits. Archaeological sites across the Americas contain mammoth bones with stone projectile points embedded in them, proving humans hunted these animals. Proponents argue that when human populations equipped with advanced hunting technologies encountered naive prey animals that had never faced human predation, the result was catastrophic overkill. Critics of the overkill hypothesis point out that evidence for intensive megafaunal hunting is surprisingly sparse. While kill sites exist, they're relatively few considering the continental scale and multi-thousand-year duration of extinctions. If humans hunted mammoths to extinction, why aren't mammoth kill sites everywhere? Additionally, many extinct species show little evidence of human predation. Giant ground sloths, which went extinct in South America around 10,000 years ago, left thousands of fossils, but few show signs of human hunting. The extinction of carnivores like saber-toothed cats is particularly difficult to explain through overkill. Humans rarely hunt large predators for food. The climate change hypothesis proposes that environmental shifts at the end of the last ice age drove extinctions by altering habitats and vegetation. Between 20,000 and 10,000 years ago, global temperatures rose by 9 to 11 degrees, ice sheets retreated, sea levels rose by 400 feet, and precipitation patterns shifted dramatically. In northern latitudes, productive steppe tundra grasslands that had supported mammoths, horses, and bison were replaced by forests and peat bogs, offering less nutritional forage. In Australia, increasing aridity transformed landscapes. These habitat changes could have reduced carrying capacity below levels needed to sustain large animal populations. However, megafauna had survived numerous previous glacial-interglacial cycles over millions of years. Why did this particular warming event cause extinctions when earlier warmings did not? Critics point out that climate changes during earlier interglacials were equally dramatic, yet megafauna persisted. Something about the most recent transition was different, and the presence of human hunters represents the most obvious novel factor. The synergy hypothesis proposes that climate change and human hunting combined to drive extinctions. Climate shifts stressed populations by reducing habitat and food availability. Already stressed populations were then pushed to extinction by even modest hunting pressure. Neither factor alone might have caused extinction, but together they proved fatal. This hypothesis explains why some species went extinct while others survived. Those that could adapt to changing climates or avoid human hunters survived, while those facing both stresses simultaneously perished. Evidence from individual species provides nuanced pictures. Woolly mammoths survived on isolated Arctic islands until 4,000 years ago, long after mainland populations vanished, suggesting that human hunting, not climate alone, drove continental extinctions. However, genetic studies show that mammoth populations were declining and losing genetic diversity for thousands of years before final extinction, consistent with climate stress. Ground sloths in South America persisted through multiple climate cycles, but disappeared shortly after human arrival, suggesting hunting played a role. Cave bear extinctions in Europe occurred during periods of climate warming that reduced cave availability, crucial to their hibernation, suggesting environmental factors dominated. The disappearance of megafauna restructured ecosystems in profound and lasting ways. Large herbivores shape landscapes by consuming vegetation, dispersing seeds, trampling soils, and creating patches of disturbed ground. Their removal allowed woody plants to expand, changing grasslands and savannas into forests in many regions. Without large herbivores maintaining open habitats through grazing and browsing, fire regimes changed. Some researchers propose that megafaunal extinction contributed to increased atmospheric CO2 concentrations at the end of the Pleistocene by allowing forest expansion that altered carbon cycling predator-prey. Relationships collapsed when large prey disappeared. Saber-toothed cats, dire wolves, and short-faced bears lost their food base and went extinct. Scavenging birds like teratons, condor relatives with 16-foot wingspans, vanished when large carcasses became rare. The ecological cascades from megafaunal extinction rippled through entire ecosystems, affecting organisms from insects to plants to small mammals. The late Pleistocene extinctions represent a global catastrophe driven either partially or entirely by human actions. Whether through direct hunting, habitat modification through fire use, introduced diseases, or interactions with climate change, human populations expanding across the world coincided with the disappearance of most large animals. This makes the megafaunal extinction the first and one of the most severe examples of human-driven environmental change, fundamentally altering Earth's ecosystems millennia before agriculture or civilization emerged. Between 183 and 93 million years ago, during the Jurassic and Cretaceous periods, Earth's oceans repeatedly developed massive dead zones where hydrogen sulfide poisoned waters and oxygen vanished. These oceanic anoxic events, OAEs as geologists abbreviate them, occurred at least 5 times, each lasting hundreds of thousands to millions of years. During OAEs, vast volumes of seawater became hostile to most marine life, creating conditions where only specialized bacteria could survive. The events left distinctive signatures in rock formations worldwide. Thick layers of black, organic-rich shale deposited when dead organisms accumulated in oxygen-free waters that prevented decomposition. These black shales now constitute important petroleum source rocks, but they originally formed during episodes of planetary-scale ocean suffocation that killed massive numbers of marine organisms and restructured marine ecosystems. The causes involved complex interactions between volcanic activity, orbital variations in Earth's rotation and tilt, climate warming, and nutrient cycling, creating feedback loops that transformed oceans from oxygen-rich to oxygen-depleted states over millennia. The best-studied oceanic anoxic event occurred approximately 93 million years ago, spanning the Cenomanian and Turonian stages of the late Cretaceous, designated OAE2. Geological evidence shows that this event lasted roughly 500,000 years, during which organic-rich black shales were deposited in ocean basins worldwide. The trigger appears to have been massive volcanic eruptions forming the Caribbean Large Igneous Province, flood basalt similar to the Deccan Traps but erupted underwater as the Caribbean Oceanic Plateau formed. These eruptions released enormous quantities of CO2, causing greenhouse warming that raised ocean temperatures by 5 to 9 degrees Celsius. Warmer water holds less dissolved oxygen than cold water, a basic physical principle with catastrophic biological consequences. As oceans warmed during OAE2, oxygen concentrations dropped. Simultaneously, warming increased weathering rates on land, washing nutrients including phosphorus and nitrogen into the oceans. These nutrients fertilized explosive algal blooms. When algae died and sank, bacterial decomposition consumed remaining oxygen, creating anoxic zones that expanded from seafloors upward into the water column. In the most severe phases, anoxic conditions reached shallow shelf, environments where most marine life concentrated. Chemical evidence from black shales, deposited during OA2, reveals that conditions became not merely anoxic but euxinic, meaning hydrogen sulfide accumulated in the water. Hydrogen sulfide forms when bacteria in oxygen-free environments use sulfate instead of oxygen for metabolism, producing H2S as a waste product. This gas is toxic to most oxygen-breathing organisms at concentrations exceeding a few hundred parts per million. Finding biomarkers from purple and green sulfur, bacteria, organisms that photosynthesize using hydrogen sulfide instead of water in rocks representing shallow marine environments indicates that toxic conditions extended throughout much of the ocean. Marine organisms faced multi-layered stresses. Warming waters approached thermal tolerance limits for many species. Oxygen depletion suffocated those requiring well-oxygenated water. Hydrogen sulfide poisoned survivors, and ocean acidification from dissolved CO2 made shell building difficult for calcifying organisms. Extinction rates during OAE2 exceeded 25% for some groups including planktonic foraminifera and certain mollusks. Fish populations crashed. Reef ecosystems declined. The marine food chain, from phytoplankton to apex predators, experienced severe disruption. Yet OAE2 wasn't unique. The Torsian oceanic anoxic event occurred 183 million years ago during the early Jurassic, triggered by volcanism forming the Karoo-Ferrar Large Igneous Province in southern Gondwana. The Aptian OAE around 120 million years ago corresponded with eruptions forming the Ontong Java Plateau in the Pacific. Each event followed similar patterns: volcanic CO2 release, greenhouse warming, nutrient mobilization, algal blooms, oxygen depletion, and accumulation of organic-rich sediments. The recurrence of OAEs throughout the Mesozoic indicates that Earth's ocean climate system can repeatedly flip into anoxic states when carbon injection rates exceed certain thresholds. Recovery from oceanic anoxic events required burial of excess organic carbon in sediments, removing carbon from the ocean atmosphere system, and restabilization of ocean circulation. This process took hundreds of thousands of years. During recovery phases, ocean chemistry gradually returned toward normal. Oxygen concentrations increased, and hydrogen sulfide concentrations declined. Marine ecosystems rebuilt, though communities that emerged after OAEs often differed substantially from those that existed before, reflecting both extinction-driven losses and evolutionary changes in surviving lineages. The black shales deposited during OAEs contain up to 30% organic carbon by weight, far higher than typical marine sediments with 1 to 2% organic content. This extraordinary accumulation occurred because oxygen-free conditions prevented bacteria from consuming organic matter. Instead of decomposing and releasing nutrients back into the water, dead organisms accumulated on the seafloor and became buried. Over millions of years, heat and pressure transformed this organic matter into petroleum. A significant fraction of the world's oil and gas reserves formed from organic matter deposited during Mesozoic oceanic anoxic events, making these ancient catastrophes economically valuable in modern times. Understanding OAEs helps scientists assess risks of modern ocean deoxygenation. Contemporary oceans are losing oxygen as warming reduces solubility, and as agricultural nutrient runoff creates expanding coastal dead zones. While current changes operate on faster timescales and smaller spatial scales than Mesozoic OAEs, the underlying mechanisms, warming-driven oxygen loss amplified by nutrient loading, are fundamentally similar. The ancient events demonstrate that once anoxia becomes established, positive feedbacks can sustain and expand oxygen-depleted zones for hundreds of thousands of years, making recovery slow even after triggering factors cease. Oceanic anoxic events represent recurring planetary-scale disasters where Earth's ocean climate system crossed critical thresholds into hostile states. These events restructured marine ecosystems, drove significant extinctions, and required hundreds of thousands of years for recovery. They demonstrate that oceans, despite their vast size, are vulnerable to disruption when carbon enters the system faster than natural processes can remove it, and that the consequences of such disruption persist on geological timescales far beyond human experience or planning horizons.